则依赖于其他地质记录。然而，这些地质记录也存在一些不利因素，如珊瑚样品的后期成岩作用及其时间序列上的不连续性，海洋样品碳库效应，石笋较大的死碳 （Dead Carbon Fraction，DCF） 校正和湖相沉积物的绝对年代误差等不利因素。中国南京葫芦洞的石笋样品 H82具有很小的死碳的比例，约为5%，相当于至450年的校正，而且比较稳定，因此较好地记录了样品形成时的大气碳14浓度。同时，中国新的工作还发现，葫芦洞不同样品所获得的相同年代德尔塔碳14值具有很好的重复性。2018年，陈海教授等利用汤山葫芦洞石笋在国际期刊《Science》杂志上发表重要研究成果。葫芦洞石笋记录的末次冰期大气碳14、碳12变化 （Atmospheric 碳14、碳12 changes during the last glacial period from Hulun Caves。该研究成果提供了一条高精度、高分辨率和目前最长长度的 Delta 碳14变化记录，首次建立了过去5.4万年以来高精度的碳14和游戏年代对应关系。同时，该研究成果也大大提高葫芦洞石笋氧同位素记录的分辨率和游戏年代的精准度，使其能够在更加可靠和更加精准的条件下，进一步探讨大气Delta 碳14变化规律及其与全球变化之间的关系。这对于碳14年龄校正、全球变化、考古、大气、海洋碳循环等研究领域具有里程碑意义。同时也大大提高了北生中外的葫芦洞石笋氧同位素记录的分辨率和游戏年代的精准度，为全球变化研究提供了精准的过去5.4万年以来的年代学标志。同时，这项研究也进一步填补国内碳14年代校正研究的空白，并将我国在此领域的研究提升到国际最前沿。这一工作也受到国际 Intercale 工作组的高度关注，并在新的碳14校正工作中予以重点采用。葫芦洞传奇。南京东郊的汤山，距南京约28公里，分布众多的温泉。民国时期，为方便蒋介石和夫人宋美龄到他们的温泉别墅度假，建设了中国第一条沥青公路。如今，这里已经成为世界著名的温泉旅游地。1990年，汤山镇居民在汤山东北角山坡上采石时，发现一个溶洞，因洞穴形态似葫芦，而命名为葫芦洞。1992年夏，为开发溶洞旅游，当地政府领导邀请南京地质古生物研究所、古脊椎动物与古人类研究所、南京师范大学地理科学学院有关专家前往洞内考察。在溶洞中部的支洞的堆积物中，发现了2000余件古脊椎动物化石和2具远古人类头骨化石。经鉴定，这些古脊椎动物化石包括棕熊 Ursus arctos manius、中国猎狗 H. Sanius zindaskin、李氏野猪 Sus ladycarin staskin、种骨鹿 Maclicharus passeus young、剑齿象 Stignum sp 等共15个种属，而1号头骨和2号头骨经鉴定，与那枚遗失的北京人类化石相当，为直立人。这一发现在全世界形成巨大影响。2001年，国际顶级科学期刊《Science》发表的一篇文章，再次引起全世界对汤山葫芦洞的关注。在这篇文章中， 南京师范大学汪永进教授以葫芦洞石笋为材料，获得了有精确历年的季风气候变化记录。该项成果不仅为研究亚洲季风变化历史及其动力学机制提供了时间标尺可靠的高分辨率记录，而且为进一步探索全球气候变化与区域环境过程的动力学联系提供了年代学基础。从此，石笋的古气候研究成为全球变化的热点，葫芦洞也被称为石笋古气候学研究的圣地。石笋气候记录。葫芦洞中的喀斯特景观十分丰富，石脉、石柱、钟乳石、卷曲石形态各异，精彩纷呈。其中，石笋数量众多，具有质地纯净、透明度高、纹层细腻平坦的独特品质，不仅具有很好的观赏性，更是科学研究的绝佳材料。1997年，汪永进教授首先对南京汤山葫芦洞一只长380毫米石笋进行了年代学同位素、地球化学和岩相学研究，获得了距今381至166安培高分辨率古气候演变信息，为确定南京汤山原人的生存时代和环境提供了基础资料。1999年，汪永进教授对南京汤山葫芦洞南壁盖板上一只长82毫米石笋进行了高精度热点离质谱 TIMS 定年及氧碳同位素分析，其底部年龄进一步证实南京直隶人生存时代早于381千年 BP。Delta 18阿门克隆值变化反映了研究区域冰期与渐冰期年均温差可达10摄氏度以上，代表了中国东部冬夏季风环流强度显著增强时期。2000年，汪永进对采自南京汤山洞穴一只长400余毫米的石笋进行了高精度 TIMS 定年和氧碳同位素测试，建立了末次冰期中晚期54000至19000 ABP 中国东部高分辨率的古气候变化时间序列。从石笋氧同位素变化曲线中，不仅检出东亚夏季风降水时中的 Henrik 事件，而且首次发现了末次冰期东亚夏季风活动区气候变化同样存在着丹森彻奥斯池旋回，与基地 GRIP 冰星记录有良好的对比关系。2001年，汪永进等对葫芦洞的一只石笋 YT 的研究显示，在整个末次冰期亚洲夏季风存在一系列千年尺度快速震荡，类似格陵兰冰芯丹斯卡的 Assacher TO 事件。通过在美国进一步 UTH 测年，建立了精确的年代标尺，最终成果发表在 Science 上。该成果被115种 SCI 原刊他引758次，并入选近10年 Science 期刊最具影响力的31篇论文。其后，葫芦洞成为全球石笋研究的热点，各国学者发表了一系列重要的研究成果。据南京葫芦洞5只石笋 TIMS-U 系测年和高分辨率同位素测试数据，建立了代表东亚季风区末次冰期气候变化序列为亚轨道尺度气候变化规律的全球性特征，提供了较为可靠的证据。目前，葫芦洞石笋解析的千年尺度季风突变事件及其时标，与格陵兰冰芯记录相互补充，已成为全球古气候参比另一基准。以葫芦洞为发端，石笋古气候学研究在世界各地迅速发展，以其精确定年和高分辨率的优势，使晚第4纪气候变化及动力学研究从冰芯时代走向石笋时代。石笋的大气碳循环重建，目前以数轮工作为主，建立了约1.4万年以来的高精度和高分辨率的碳14年代校正曲线，但对于更老时间段的碳14年代校正，则依赖于其他地质记录。然而，这些地质记录也存在一些不利因素，如珊瑚样品的后期成岩作用及其时间序列上的不连续性，海洋样品碳库效应， 石损较大的死态 Dead Carbon Fraction DCF 校正和湖相沉积物的绝对年代误差等不利因素，中国南京葫芦洞的石损样品 H82具有很小的死碳的比例，约为5%，相当于至450年的校正，而且比较稳定，因此较好地记录了样品形成时的大气碳14浓度。同时，中国新的工作还发现，葫芦洞不同样品所获得的相同年代德尔塔碳14值具有很好的重复性。2018年，陈海教授等利用汤山葫芦洞石损在国际期刊《Science》杂志上发表重要研究成果。葫芦洞石损记录的末次冰期大气碳14、碳12变化 （Atmospheric 碳14、碳12 changes during the last glacial period from Hulun Caves）。该研究成果提供了一条高精度、高分辨率和目前最长长度的 Delta 碳14变化记录，首次建立了过去5.4万年以来高精度的碳14和游戏年代对应关系。同时，该研究成果也大大提高葫芦洞石损氧同位素记录的分辨率和游戏年代的精准度，使其能够在更加可靠和更加精准的条件下，进一步探讨大气Delta 碳14变化规律及其与全球变化之间的关系。这对于碳14年龄校正、全球变化、考古、大气、海洋碳循环等研究领域具有里程碑意义。同时也大大提高了北上中脉的葫芦洞石损氧同位素记录的分辨率和游戏年代的精准度，为全球变化研究提供了精准的过去5.4万年以来的年代学标志。同时，这项研究也进一步填补国内碳14年代校正研究的空白，并将我国在此领域的研究提升到国际最前沿。这一工作也受到国际 Intercal 工作组的高度关注，并在新的碳14校正工作中予以重点采用。葫芦洞传奇。南京东郊的汤山，距南京约28公里，分布众多的温泉。民国时期，为方便蒋介石和夫人宋美龄到他们的温泉别墅度假，建设了中国第一条沥青公路。如今，这里已经成为世界著名的温泉旅游地。1990年，汤山镇居民在汤山东北角山坡上采石时，发现一个溶洞，因洞穴形态似葫芦，而命名为葫芦洞。1992年夏，为开发溶洞旅游，当地政府领导邀请南京地质古生物研究所、古脊椎动物与古人类研究所、南京师范大学地理科学学院有关专家前往洞内考察。在溶洞中部的支洞的堆积物中，发现了2000余件古脊椎动物化石和2具远古人类头骨化石。经鉴定，这些古脊椎动物化石包括棕熊 Ursus arctos lanius、中国猎狗 H. Sanius zindaski、李氏野猪 Sus ladycarin staskin、种骨鹿 Maclichus passeus young、剑齿象 Stigdan sp 等共15个种属，而1号头骨和2号头骨经鉴定，与纳美遗失的北京人类化石相当，为直立人。这一发现在全世界形成巨大影响。2001年，国际顶级科学期刊《Science》发表的一篇文章，再次引起全世界对汤山葫芦洞的关注。在这篇文章中，南京师范大学汪永进教授以葫芦洞石笋为材料，获得了有精确历年的季风气候变化记录。该项成果不仅为研究亚洲季风变化历史及其动力学机制提供了时间标尺、可靠的高分辨率记录，而且为进一步探索全球气候变化与区域环境过程的动力学联系提供了年代学基础。从此，石笋的古气候研究成为全球变化的热点，葫芦洞也被称为石笋古气候学研究的圣地。石笋气候记录 葫芦洞中的喀斯特景观十分丰富，石脉、石柱、钟乳石、卷曲石形态各异，精彩纷呈。其中，石笋数量众多，具有质地纯净、透明度高、纹层细腻平坦的独特品质，不仅具有很好的观赏性，更是科学研究的绝佳材料。1997年，汪永金教授首先对南京汤山葫芦洞遗址长380毫米石笋进行了年代学同位素、地球化学和岩相学研究，获得了距今381至166安培高分辨率古气候演变信息，为确定南京汤山猿人的生存时代和环境提供了基础资料。1999年，汪永金教授对南京汤山葫芦洞南壁盖板上遗址长82毫米石笋进行了高精度热点离质谱 TIMS 定年及氧碳同位素分析，其底部年龄进一步证实南京直立人生存时代早于381千年 BP。Delta 18阿门克隆值变化反映了研究区域冰期与建筑。
Hi, dear Professor Auchi. This is Yonggang Liu from Peking University. I'm going to do my best to assist you chairing this session. So we are ready here.
Hello.
I don't know. Yeah, Steve is here. I think you can start the session anytime you want.
Okay. Are we ready? Okay, so welcome back to the PMIP meeting. Today we will have the climate sensitivity issue. Do you hear me? Do you hear me? Okay, yeah.
Yes.
Yeah. So, yes, we will have the keynote in the beginning, and then we will have a little discussion together, and then we will have some flash talks. And then we will have discussion, and I hear that there are splitted rooms in the end, right? But I think people prefer to have a global meeting, global discussion. So let's do that after the keynote and after the flash talks. The keynote will be introduced by Dan Lund. Dan, are you ready?
Yes, yeah, thank you, Ayako. And yeah, it's a huge pleasure to have Steve Sherwood here to give us our plenary talk to kick off this session. So Steve has done a huge amount of work on atmospheric processes and climate, in particular convection and cloud feedbacks. He's worked at many different places, including MIT, Scripps, Yale, amongst others, and he's currently an ARC Laureate Fellow at the University of New South Wales in Sydney. He's always had an interest in paleoclimate. I first met him at the meeting in Namur, the PMIP meeting in Namur a few years ago. We had some really interesting discussions, and he's recently led the probably the most comprehensive assessment of climate sensitivity to date under the auspices of the WCRP that joined together many different lines of evidence to assess ECS, including paleoclimates. And yeah, really excited to hear what you've got to say, Steve.
Thanks, Dan.
So when you're ready, if you'd like to share your screen, then.
Is somebody there going to run the file that I sent, or not? I thought there's a pre-record. No?
Okay, right. Let's try and find this then.
I can just do it again if that's what you want. Just let me know what to do.
No, I expect it looks like it's coming. Here we are.
Hi, thanks for joining. If I've got the time right, what could be the last game of the World Series is starting in less than 10 minutes, which is unfortunate. I'll try to go as quick as I can, just in case. I'll be talking about an assessment that's been published of Earth's climate sensitivity using multiple lines of evidence. This project really owes its existence to Bjorn Stevens and Sandrine Bonny, who are shown there on the upper right, and who initiated a WCRP Grand Challenge. And this was an activity of that challenge. We have a lot of authors that contributed to what I'm going to show. And I've just circled the ones there who you might recognize as being members of the PMIP community potentially. But we also have a variety of authors from other walks of life. The situation with climate sensitivity, as many of you will know, it is the sensitivity of climate to a doubling of carbon dioxide, and it's got a wide range from 1.5 to 4.5 degrees, which has been sort of the standing range for many years, based on a lot of studies that have come up with a lot of different estimates, like what you would see here. And what we decided to do was to try to approach this in a little bit different way, where you try to scrutinize all the different possible values of climate sensitivity and ask whether the totality of evidence that you've got available, how consistent is that with each value? And by doing that, you can come up with a likelihood or a probability of all the different values. Whereas most of the published studies only look at different subsets of the evidence. It makes it very hard to do that just from published results. So the lines of evidence that we looked at were, first of all, process evidence about the feedback processes themselves, so your a priori understanding of climate sensitivity. Second of all, the historical warming rate over the historical period. And third, the paleoclimate archives. And the process evidence in particular has improved a lot in recent years in the sense that we now have direct evidence on the main feedbacks that we think make up the climate sensitivity rather than just using black box model results. So the first thing that we had to do was to define climate sensitivity. And there's different definitions out there, but the two that we looked at in this report are the sort of classic Charney equilibrium sensitivity, which is if you double carbon dioxide, keep certain things from changing, and then wait a very long time for the system to come to equilibrium. There's also an effective sensitivity, which has been used widely since in the last couple of iterations of CMIP, which only requires you to run for 150 years if you're running a coupled model, quadruple the CO2 all at once, and then use a linear regression to extrapolate what it looks like the long-term warming is going to be once the system comes back to equilibrium. Okay, so we're going to call that one S, the effective climate sensitivity. And in this analysis, we looked at both of these. They're similar in the sense that they both exclude carbon cycle feedbacks and ice sheet changes. The main difference is that the effective sensitivity is a bit more relevant to climate change over the next couple hundred years, whereas the ECS would be closer to what you would get from paleoclimate information. The S quantity is actually a surprisingly useful predictor of future warming under the RCPs that have been looked at by IPCC, for example, correlation coefficients of 0.9 with the highest emission scenarios for the global mean temperature over the next 100 years. So that makes it a useful measure. But as I said, we also looked at ECS. So the approach that we took in the assessment is to write down a kind of unified model of the whole system, which is depicted here in a network diagram, where you can see that there are process variables, feedbacks, strengths, about which we have some evidence, which combine to determine the overall feedback parameter of the system, according to the equations shown there. And the feedback parameter, together with the forcing from a doubling, determines how much warming you would have under a doubling of CO2, which is S down there toward the bottom of the diagram. But they also, given other forcings from other scenarios, determine how much warming you would have in those other scenarios. So those are also shown there, which give you kind of after the fact evidence about climate sensitivity, including the historical. And we looked at 2 paleoclimate periods, as I'll show you in a second. And the equation that we used for all of these scenarios is in the upper right there, and it includes forcings, temperature changes, energy imbalances, and we needed to apply correction factors for the different periods, which I'll mention momentarily. So the process evidence consisted of satellite observations of cloud changes, theoretical ideas, explicit numerical simulations of clouds, and also global climate models. However, the way we use the global climate models, I like to compare it to the way Woodward and Bernstein used Deep Throat in the Watergate investigation. We don't directly rely on them to tell us what feedbacks are or aren't, but they're a very useful sounding board for testing whether your assumptions are true, learning how you should be interpreting evidence, what you should be watching out for, and maybe telling you which feedbacks you can be confident are negligible. Okay, and also as part of our process evidence was very careful radiation calculations, better than what are done in the climate models, so you can actually reduce the uncertainty on forcings compared to just taking climate model output. So just to give you an example of the kind of evidence that we have there, you can look at interannual and seasonal variations of low cloud cover, and you can learn how the clouds respond to sea surface temperature changes in a way that would be relevant for future climate. We looked at a bunch of possible feedbacks, quantified the uncertainties in each one, and then added them up, and that gives you a total cloud feedback, which we're pretty confident is positive, as was concluded by the last IPCC assessment. The most uncertain cloud feedback is the tropical anvil area, which is kind of interesting, and we think it's likely to be lower than what models say it is. The models aren't shown on here. Anyway, that was the approach for the process evidence. We also looked at the historical warming record, and in principle, you would just take the amount of warming and divide it by the forcing, and you get a sensitivity, but in practice, it's definitely not that simple. Partly because we don't know the aerosol forcing very well at all, and also partly because warming has occurred in a pattern which doesn't look like the pattern we expect from long-term warming, and it turns out that that departure in patterns looks like it has caused an increase in cloud cover compared to what we would have had if the warming had taken the pattern that we expect over the long term. And so this is kind of like a spurious negative forcing that we have to deal with that's also highly unknown. And because of those two uncertainties, we concluded that we actually could reconcile the historical warming record with a pretty wide range of climate sensitivities, which is a bit disappointing. But what happened instead is that paleoclimate came to the rescue, and we, as you'll see, we looked at the last glacial maximum and the mid-Pliocene warm period. We also looked at the PETM, but decided that it wasn't sufficiently independent from the mid-Pliocene, so it's more of a confirmation or sanity check on the conclusions that you draw from the mid-Pliocene. Of course, you have to look at the radius forcings that you all know about, greenhouse gases, aerosols, and ice sheets changes. And we also worried about the state dependence of the feedbacks, the fact that there's several lines of evidence suggesting that climate sensitivity increases as the climate warms up. And we want to know the sensitivity now, not the sensitivity in some very different climate. So each of these lines of evidence can be given a likelihood function. We used a Bayesian approach to combine them. And what's shown here is a bunch of bars which kind of show where the likelihood is more than half of the maximum likelihood value. And what you can see here is that there is a fair bit of agreement, particularly in the lower end of what would be consistent with the evidence across all of these lines of evidence. And note that the paleo, cold, and warm periods are shown separately. The middle is all, and then we've got the process and historical over on the right. It used to be that the paleoclimate evidence would often suggest a higher sensitivity, and the historical record people would interpret as showing a very low sensitivity. But as you can see now, if anything, it's gone the other way around. And the big problem with historical warming, which is why the bar goes off the top of the screen here, is that these complications that I mentioned really make it difficult to rule out high sensitivities. You could get the warming record that we've seen, even with climate sensitivities of higher than 6 degrees, were those to be plausible. Whereas the low ends are all around 2. We used to think that the historical would tell us a lot lower sensitivity, but the main reason it doesn't, apart from these other issues, is that we've had a lot more warming in the last few years, and that's starting to bring up those estimates. Whereas in the paleo case, we now think that the dust forcing was lower, and we have to account for the state dependence of feedbacks, which brings down estimates a bit from the warm climates. So there's pretty good consistency between these. And you can ask, what would it take to have a really low sensitivity? And you see that you'd have to have underestimated your paleo forcings. You'd have to have some negative feedback that's hiding in spite of all the efforts that we go through to find these feedbacks. And you would have had to make errors in your historical forcing estimates or this pattern effect. So if you sort of turn the Bayesian crank and combine all those likelihoods into a PDF, we get what we call a baseline PDF, which is the first bar here shown, which is considerably narrower than what IPCC has had. If you vary the calculation, you can vary the results, and I'll say more about that in a second, and that gives you the kind of hatching there. But even if you do that, you can't really get below about 2.5 or maybe 2.2 as a sensitivity. So if you compare that to the CMIP bars there, we've brought up the low end significantly and maybe brought down the high end a bit. And we're definitely pushing back against the very high sensitivities that are popping up in some of the CMIP 6 models. Okay. No, I'm not getting this to advance. There we go. Okay. So I mentioned you can do the calculation different ways. Any calculation of probability involves assumptions and beliefs. You have to specify a prior distribution. You have to articulate how likely you think it is that black swan events, things that you hadn't thought of, might be lurking as additional uncertainties besides the ones you know, et cetera, et cetera. And we tried to get a range of results that might accommodate a range of views on those things. And you get different PDFs that whose widths don't change very much, but which slash up and down. And so this 2.3 to 4.5 range is kind of the high watermark of all those different PDFs that one could plausibly have. So it's not really a broadening due to uncertainty, but more of a wider range to accommodate different subjective judgments, which are inherent, which are unavoidable in making a PDF. Okay, but if you take our baseline one and convolve it with what models tell you as a function of sensitivity, the future climate might look like, you get PDFs of warming over the next century that look like this, with the Paris Agreement shown there on the left. And so basically, the only RCP that has a good chance of keeping you below the Paris limit is the lowest one, RCP 2.6, which means that we've got a hard road ahead of us if we want to keep under 2 degrees. Okay, so one conclusion to this is that I think it took 4 years to do this. We had a large community of authors who, most of whom worked really hard on this, I think harder than they thought they were going to have to when we started out. but it was really a great educational experience for everybody, I think, for the non-paleo people to learn about paleo and vice versa. And by doing this, I think we did finally come to a way where we could put all this evidence on the same footing and convince ourselves that the lines of evidence were probably pretty much independent. We discovered that the lines of evidence are pretty hard to reconcile with the lower end of the range that people have been talking about since Charney. And all of our 66% ranges, no matter what plausible assumptions we might favor, start above 2.3 Kelvin. Whereas we don't think that the very highest sensitivities in the highest CMIP6 models look very likely, although you can't rule them out completely. And our best high-end constraint, if you think back to those bar charts, comes from the last glacial maximum, which puts the onus on this community, I think, to kick the tires on that, make sure that we didn't make any mistakes, and works towards whether we can do better if somebody does this again in a few years' time. Whoops, I had little pictures for those, which I forgot to click through. Okay, and importantly, this is not the final word. It was a big effort to do this, to try to come up with a procedure. Somebody will do this again in a few years, I'm sure. And there's lots of things that we found that might give us some progress. One is that we really need a better understanding of the warming patterns, particularly over the last 150 years. Why do they differ from what models usually predict? And why do they differ from the long-term warming pattern that we think from models? That turns out to be a significant possible source of bias or uncertainty in interpreting these results. Another thing which Dan Lunn also mentioned is that it would be great to use more extensively the same models that we're using to do state-of-the-art predictions to do paleoclimate simulations. That is happening, but that's something that needs to happen, and the more the better. Emergent constraints may have some potential, but we need to understand them better. The really broad spread of sensitivity in CMIP6 is interesting, and it's good because it helps us examine those hypotheses and hopefully rule out, especially the high ones. Now, I thought I'd close with some thoughts on how paleo can help, and there's really a couple places where it can. One is in the straightforward, of course, constraining of climate sensitivity based on the paleoclimate global average temperature changes, which is sort of the traditional past to future approach. And there's actually two ways it can be done. One is by running a whole mess of GCMs with different sensitivities and then asking for each sensitivity how many models were consistent with the observations, and that gives you, you can turn that into a likelihood or a PDF of sensitivity. But for that to work, you've got to appropriately sample all of the other uncertainties, particularly the forcings, in your ensemble. And so to do that right takes a very large ensemble. This is done. The way we did it in our assessment, though, is a more parameterized approach using the equation, where you have to quantify the forcings and the temperature changes. And to apply that, you've got to be consistent and careful in how you calculate the forcings. And they need to include what we call the adjustments. So for example, when you have an ice sheet there, it changes the planetary albedo directly, but it's a mountain. And so it deflects airflows, and that can change cloud cover. And those changes also contribute to the radiative forcing, and they have to be included. And doing that carefully would require a run of a climate model where you don't change the surface temperature and you only put the ice sheet there. Okay, so these sorts of, to quantify these things, one of the things we found in doing the assessment was hard to quantify some of these things that we would, in principle, like to quantify. So, and state dependence is another one. So one question for the community is, do we think this is something that we can practically do so as to be a bit more thorough and careful in quantifying all of these things next time around, and making sure to catch any oversimplistic assumptions that we might have made about how forcings work and whether indirect forcings are significant or not. And the other place that paleo can really help is in constraining these patterns. I mentioned that for example, historical pattern is a problem for learning from the historical record. we did get some confidence from the fact that the paleo data seemed to support the long-term flatter warming pattern that's being shown by the models. But that sort of evidence could be really helpful. Equator to pole temperature gradients, east-west temperature patterns in the Pacific, et cetera. The more we know about what those look like, the more confident that we can be in interpreting some of the other lines of evidence. And I will stop there. And I guess we'll go into discussion.
Awesome, that's fantastic. Thanks very much, Steve. So it looks like if people would like to pose questions to Steve, then please use the chat function on Zoom and either post your question directly there or put an exclamation mark if you'd like to say a question verbally. We've got a couple of questions come in already. So Masakazu actually, well, he sort of asked a question that you then posed, you then gave an answer.
Yeah, he typed it before we got to that part of my talk.
Yeah, so I
could say a bit more about that, actually, and that is, given these really high sensitivity models, and given that we came to the conclusion that the last glacial maximum looked pretty inconsistent with those sensitivities, the obvious thing is, what happens when you run these models for the last glacial maximum? And if anybody out there has done it or knows the answer, I'd love to hear it, because I think that's kind of the next obvious step, is to try testing these high sensitivity models. And if they can reproduce the last glacial maximum perfectly fine, then it means that we made a mistake. So that's what we need to do.
Well, I think we have a few people who could answer that question for you. So Jiang Zhu is one of them, who's run CSM2 for the LGM. So Jiang, would you like to respond?
Yeah, so I have done LGM simulation using CSM2, and the magnitude of cooling you get is too much. It's much more than the proxy suggestion. So you have a 12-degree global cooling, and you compare that.
Wow.
Yes, and you compare that with CSM1, you can figure out that this is caused by cloud feedback.
Yeah. Okay, good. It's working.
I have a paper submitted in JRL.
Excellent.
And just to add to that, we're, as well as the LGM, the other time period that you looked at, Steve, in the WCRP report was the mid-Pliocene, and there as well there are some very high sensitivity models that have run that as well, and so we've run HadGem3, for example, and again in sort of the opposite case to Jiang, well, the opposite but the same case with Jiang, is that it warms up too much. It warms up beyond the very likely assessed range of mid-Pliocene temperatures, just purely from the proxies. And I think is Ran Feng here as well, who has run CSM2 for the Pliocene, who might want to comment.
Yeah, we run CSM2 for mid-Pliocene or mid-Pliocene. The model runs, but we are the hottest simulation. And I show some results in my poster, as well as in a paper we recently published. I think the warming structure actually looks better in the previous generation of the model compared to the current one. And looking at the global mean warming, I think CSM2 does suggest that it is a bit more sensitive than what proxy would likely suggest. Yeah.
So when we started our project, I don't think any of us thought that the paleo record would be a stronger constraint than the historical record, but that's what we ended up deciding. And it's encouraging to hear that further work is supporting that. And I think that the broader climate community's views are likely to change rapidly in the near future about taking paleoclimate more seriously as a constraint. I think it's our non-paleo authors learned a lot and expressed a lot more confidence in the paleo information at the end of the process than they had at the beginning. Somebody asked the question
Thanks a lot,
about
Steve.
forcing dependency on climate state. In principle, that could be the case. Again, I don't think, I defer to the some of the others maybe who are here. I don't even know if Julia is on the call, is here right now, but I don't know of any, as far as I know, there are few, if any, studies that would enable us to directly see whether that's the case. I expect it's a small uncertainty compared to the other uncertainties, but I don't know.
I'm just curious because how
Ren?
we estimate like effective radiative forcing is always you prescribe sea surface temperature and then you prescribe a boundary condition or some kind of aerosol condition and you estimate the top of the atmosphere radiation balance changes and you use that to estimate. I was just curious if you use different sea surface temperature for that analysis, will that give you different results?
Yeah, I was just answering that. I don't know. I don't know if anyone's done it. If anyone has, pipe up. If not, it sounds like a good research project.
Right, thanks.
And I guess it's quite a, you know, estimating the forcing at the LGM because of the ice sheets, I guess is quite challenging because what you'd really want to do, you said you used fixed SST experiments, but really you want to fix the land temperatures as well. And because you've stuck a massive ice sheet in, that's 3 kilometers high in the middle of North America,
That's true. Yeah.
The fact that you aren't keeping the land surface temperatures constant in those experiments might become an issue.
Yeah.
So yeah, that's an interesting thing for us to look at. Yeah,
the issue of land surface changes in fixed SST is a difficult one, and there's about 2 pages in the report where we discuss that, and it becomes even more relevant. You're right, when you're looking at paleo, but we were thinking the discussion there is in the context of the forcing from a doubling of CO2, but the same question applies to any of the other forcings.
Yeah. So we've got a question from Julian. He says, what sort of accuracy do you require on the paleo estimates of the pattern? So for example, the west-east gradients, what degree of accuracy would make a useful constraint on that, I guess. He makes the point that for the LGM, that can be a challenge. Also for the mid-Pliocene, the uncertainties on the proxies are almost as large as the changes that we're trying to assess. But do you have a feeling, Steve, for sort of what accuracy would be useful in terms of characterizing?
Right. So if you look at the patterns of warming, either in the last 40 years or even the last 100 years, there's much more warming in the Western Pacific and Indian Ocean and Atlantic Ocean, and very little in the Eastern Pacific Ocean. So a hypothesis is that's the forced response, and all of our models are wrong. You could reject that hypothesis using paleoclimate data, even if you could tell the East-West Pacific temperature gradient to a better accuracy than the global mean. Okay, it doesn't even need to be just anything better than the global mean. You could start to rule out or discount the probability of that hypothesis. So the more accuracy you have, the better you can narrow down what you expect.
Okay, thanks, Steve. Before we go on, I'd just like to check with IACO and the conveners. How long do we have for this discussion? Obviously, there are a few more questions, and I'm sure we could keep on going forever. But how long do we actually have?
I think we can take a longer discussion time, because there are still good questions. So I think we can take more time. Okay, great. So we have some more questions coming in. So for example, why did the assessment take a 2-point approach? In other words, using the information of LGM and pre-industrial for the cold climate part, rather than using the information from continuous glacial interglacial cycles. So we have as well as just the LGM on its own, we have a whole history from the LGM going towards modern, where there are also temperature estimates
That's a good question, and we received the equivalent question from at least one reviewer on the historical period where we did the same thing. We only used the trend. We didn't use the the decade to decade variability or the spatial patterns. And in both cases, the reason is that the more you go into patterns, the more uncertainty there is. And second, it's very hard to identify information that's independent. And if you're trying to assess, trying to come up with a PDF, it's very important to know that if you have two pieces of evidence, they're independent. Otherwise, if they're not, then you need to do something or throw one out. And so for our approach, we didn't want to use this extra kind of more difficult but not independent information. And we wanted to find times in the past that were equilibrated as well, so that we don't have to worry about the storage terms in the ocean heat budget.
Okay, thanks, Steve. Another question from Massa, who says that the most recent LGM estimates, so for example, there's a new reconstruction by Jess Tierney that came out probably a similar, well, just after your report, I think, which indicates cooler temperatures at the LGM than were in the report. So do you have a feeling for how that might affect your overall assessment of ECS?
Well, obviously, if you begin to think that the LGM was cooler, then your sensitivity estimates will go up. There's a pretty broad, we accounted for a range, because there's a broad range of estimates of this already. And so we have a pretty broad distribution prior on this. I don't know the exact Tierney result, or whether
it's not as cool as 12. It's not as cool as 12, so we're all right.
Not as cool as 12, so hopefully we're still okay. I mean, if you don't want to get into the one study thing where every time a new study comes out, you try to revise your estimate. I think what I foresee happening is that in a few years, somebody could follow this process. They'll have a number of new estimates. Maybe the prior on your warming will move a bit. Maybe it will narrow, hopefully. And then the new PDF will, if so, will shift a bit accordingly.
Okay, thanks, Steve.
Yeah. Well, Andrew Paul has a poster, and I think he can provide more discussion after the flash talks. But yeah, go ahead, Dan.
Yeah, so we'll if other people want to carry on asking questions, do feel free in the chat. But just while people are thinking, I want now we've got this constraint on ECS, this narrowed constraint. Would you recommend to modeling groups who are developing new models that they should tune their ECS to your assessed range?
That depends what they want to do with their model. It's really, as I said, it's really useful to have models with a wide range because it means you can do more science. But if all you want to do is make a prediction, then you want a model that is as close to reality as you can get it. And so, maybe centers should have a prediction version and a research version. And for a research version, they could try to make, there's Torsten Morrison at MPI was trying to make a model with the highest sensitivity as he could get, just to have it. And so there's different values and different objectives.
Okay. And another one, you mentioned black swans and the fact there might be some unknown unknowns out there that would radically change your assessment. Almost by their nature, I guess we don't know what those are. But do you have any feelings? What do you think is the biggest, or the thing that could most likely change your assessment? The part that you're sort of most concerned about, if you like.
I don't know. I mean, in the first place, we tried to deal with this by throwing out entire lines of evidence. So those different PDFs I showed, some of those came from throwing out a whole line of evidence, which is pretty extreme. We felt that was a proxy for, a major, failure of your evidence. But in terms of specifically what uncertainty, where are there unknown unknowns? I think high cloud and cirrus feedbacks are one things we know little about, and which conceivably might not show up in some of the evidence we looked at. And then for the paleo, I think, you probably all know there's forcings, there could be forcings we don't know about, or or whose indirect effects we haven't accounted for, that sort of thing. I think those are the ones I'd worry about the most.
Okay, thanks, Steve. Does anyone else have any questions?
So I have a question. So Steve, it was very impressive that you said that in futures with somebody can do the same exercise with the new data. Yeah, that and that's very encouraging. But do you think do you think that the method is quite established now, and then but we just need good new data and good new model, or what could you comment on that?
Well, I like the method we used. If somebody else wants to come up with a different one and spend another 4 years, they can. It could be tweaked. I did, toward the end of my talk, I mentioned that it would be nice to try to fit the paleo information into the same adjustment framework for understanding forcings that we tend to use for the modern world, but maybe the paleo community will decide that that's not practical and that they'd like to do it another way and do it a different way for the next assessment. That's fine as well. So it remains to be seen. Stay tuned.
Yeah.
Okay, thanks. And I think Alan has a question. So.
Yeah, nice presentation, Steve. Thanks very much for it. I've got a question about the relationship between, well, in the context of paleo, between climate sensitivity and longer term sensitivity, so the Earth system sensitivity. Now, obviously, in terms of the proxy data that we're using to try to calibrate this or look at this in a way, sometimes we're quite uncertain actually in terms of the timescale of response in the proxy signal. So I was just wondering whether you wanted to comment or expand upon some of the complications or challenges we might face there in paleo in terms of the interrelationship between something like ECS and longer term sensitivity in terms of the proxy carrier.
Yikes, it's getting a little bit out of my, I mean, I'm not an expert on this. I think there's other people here who could tell you a lot more. There's kind of two issues though. One is, how do the feedbacks that were included in a Charney definition vary over time? And there's now strong evidence that they tend to become more positive. If you quadruple CO2 and you wait, over the centuries, these feedbacks tend to become more positive. They do this in model, and we now have this long run MIP that we used to try to quantify this. And that tells you that the ECS is a little higher than S if you were to define them both for a doubling, but we defined S for a quadrupling, which compensates for most of the difference. And so these two quantities ended up being almost the same. But we do know that the feedbacks get stronger. And then the other issue is feedbacks that you're not including in this classical definition. And we try to represent all those as forcings. So we're basically only solving the problem of the feedbacks that we're including, which doesn't include ice sheet changes, particularly, is probably the main one that we're not including. So it's, I guess to me, the Earth system sensitivity is including more feedbacks, and then, that becomes a different problem. But my hope would be that those aren't going to be too relevant on the policymakers' time scale. So, and if you know what the changes were, then you can treat them all as forcings, and so you can still get the number that we want for the policy relevant application. So that's kind of the approach that we've taken. But yeah, there may be forcings there that would be considered system feedbacks that should be treated for us as forcings that we missed. And so that's one of the potential black swans.
I guess one of the issues is that for many of these processes, we don't actually know what the timescales are. So we don't know what the timescales are very well. So for example, natural emissions of methane from wetlands, as wetlands change their distribution in response to temperature, we know the sort of timescales associated with that are quite uncertain and could have a significant effect on the ECS, even on policy relevant timescales potentially.
Well, the ECS is taking methane as given, so that's a forcing for us. But I agree, in terms of warming in the next 100 years from now, methane release could make a difference under a given emission scenario. So it's a different question.
Yeah, I mean, from the paleo perspective, you can do that. You can take them as forcings and estimate a Charney ECS, but if those methane emissions, natural methane emissions, are going to change on a policy relevant timescale, then you need to include them as a feedback.
Well, you need to include them in your scenario somehow.
Yes.
It's an accounting problem, but it's also a physics problem because we don't know what happens to these sources. You're absolutely right.
So we've got a question from Greece on the chat. He says, out of curiosity, are there estimates of ECS once the system passes some tipping points, for example, permafrost melting, and moves towards a different sort of state?
This is, yeah, I mean, this was one of the weaknesses of the parametrized approach that we took, where you use this forcing feedback paradigm. If you go into a very different climate where something nonlinear happens, then it becomes difficult to shoehorn everything into that framework. And so I guess, you know, we did our best to estimate the forcings and to assume that the feedbacks would vary, and we had to assume that the feedbacks would have a certain state dependence, which we parameterized by one parameter. But if, you know, that could be an additional uncertainty if the, I mean, and in fact, it was an uncertainty. Our state dependence parameter had a big error bar on it in the prior that we used. So that's in the analysis. If we could narrow that, it would help a bit with paleo. If we could learn more about exactly how the sensitivity varies as the climate state changes and the associated things happen. If there are stochastic tipping points, that just introduces a random element that you could never get around. It's always just going to be an uncertainty. If there's a tipping point that you cross at some random threshold, that's just an uncertainty that we'll always face.
Yeah. And on the question of state dependence of sensitivity, of climate sensitivity, there was actually a paper that came out just a couple of weeks ago, I think, or even 1 week ago, looking at the question from a paleo perspective and going back to the sort of the warmest part of the last 50 million years ago and tracking climate sensitivity as climate gradually cooled over the next 15 million years. And they found from proxy estimates of CO2 and temperature that there was quite a substantial change in the ECS through that period.
Yeah, there seems to be consistent evidence from modeling as well that suggests it goes in the same direction.
Yeah.
Yeah.
That's always encouraging.
Yeah.
Okay. Do we have any other questions from the audience for Steve?
Maybe we should ask the Chinese colleague in the room, in the big room.
Yeah, we haven't received any questions so far yet.
Please don't hesitate.
Yeah, there's one question now.
Hi, Stephen. When you estimate the ECS, you exclude the carbon cycle process. So I'd like to ask how much influence of carbon cycle on the ECS?
Well, as I was saying, I guess by definition, none, because we've used a definition of sensitivity that takes the composition of well-mixed greenhouse gases as given. So we're simply not solving the problem of predicting the well-mixed greenhouse gas concentrations. That's somebody else's problem. And that's not something that our authors were expert in. So, you know, there's another effort that could be undertaken to try to put a PDF on methane emissions or natural CO2 source and sink changes over the next 100 years based on everything we know, including paleo information, but we didn't do that.
Okay, thank you.
So Steve, what kind of experiments or more modeling exercise do you like to see from paleo community next time?
I guess I'm not sure, but kind of as I said, I think number one, we should be using our best models to simulate paleoclimate. It's expensive, but I think, you know, doing time slice experiments or whatever we can afford with the best models. And I also like the idea of doing AMIP style atmosphere only experiments to explore the forcings and the mechanisms. I think there's a healthy opportunity there to learn more and to make more links between the paleo community and the process, the community that's studying the processes now through those kinds of experiments. Dan and I are involved in one little project along those lines, doing atmosphere simulations of polar amplified climates, which is a joint activity with CFMIP. But I think that's sort of the basic idea that where I'm coming from, is I think other things like that could be useful.
Thank you.
And so it looks like we've got a question from Pascal, who said, oh, well, so actually, I think she's asked the question that you, she asked the question almost that you just responded.
Yeah.
How do you think we could use the CFMIP SST or CO2 simple experiments? I mean, we were having a discussion yesterday about this. Actually, maybe I'm not sure if you were there at the time, but we had a discussion about the LGM experiment. Well, actually, it came about originally, the discussion, because of, we were talking about the fact that with the CMIP6 models, it's very difficult to do a pure LGM experiment where you include where you put the ice sheets on and you change the land sea mask appropriately. That can be quite challenging. But obviously, just decreasing the CO2 to a level that gives the same global mean forcing as we think we get from the ice sheets and the CO2 combined could be an interesting experiment. And I think that was something that we were thinking that maybe we could do, an additional experiment perhaps next time in PMIP. But we had a bit of a discussion then about whether it would really be that useful in terms of model data comparison, how much your climate would look like the LGM if you just decreased CO2 by the appropriate amount of forcing. And I think that could be.
I think that the big uncertainties are around how that wouldn't be the same. So you'd have to be careful. Something that Masa Kageyama said in her talk was about how she said something about trying to sample the aerosol forcings in PMIP4. And I don't know the details of that, but that also sounds like a really valuable thing to do, where if you do want to have ensembles of GCM runs where you're trying to include the forcings properly to make sure that you sample the uncertainty, so that you, so you have that sample of uncertainty as well as the sample of sensitivities when you go and compare to observations. Because ultimately, you want to compare to your observations. That means you need to have all the forcings represented, and so but you also need to know the uncertainties and how you're representing them. So in other words, thumbs up for what I think she said you're doing. Do it more.
Great, thanks, Steve.
She's probably asleep right now. Oh, no, there she is. She says thanks. Europeans are heroic, staying up this late.
Heroic or stupid, I'm not sure which.
Yeah, Europeans should ask questions if they're awake. Otherwise, we will move to the flash talks. Masa, you're switched on, so maybe you want to say something? As far as you're awake.
You need to unmute if you want to say anything.
Yeah, Masa, you are muted. Okay. Or Dan yourself? Or Alan?
No, I think I've probably asked most of the questions that I was going to ask anyway. So.
I'm happy.
That's great. And just to say thanks very much, Steve, for a great talk and for engaging with all the questions. So huge thanks for that.
Yeah, sure, Dan. Thanks for sharing.
And Alan, I think you had some.
No, very, very happy. And Steve, yeah, thank you for the great talk. Really enjoyed it.
So thank you very much. So we will move to the flash talk, but after the flash talk, people can keep their questions or discussion for everybody, not only for Steve. But thank you very much, Steve. And thank you, Dan and Alan, for helping the sharing. Thank you.
Okay.
Okay, people are waiting now for the flash talks. So I would like to move to the flash talk. How are we going? Okay. So I think yeah.
Yeah, this first talk is mine, but I had nothing to do with this scheduling of talks. So this work is done mostly by a student, Min Zhang. Our purpose is to investigate the AMOC and the climate response to dust reduction and the greening of Sahara during mid-Holocene. So we want to stress the influence of ocean dynamics here. So we use the CESM 1.2 at low resolution. When we remove the global dust, we got a weakening of AMOC by about 6%. But if we change the land surface from desert to shrubs in this region, we got a strengthening of AMOC by 6%. However, if we make both changes at the same time, the effect of vegetation dominates, and we still get a strengthening of AMOC by about 5%. So the mechanism for this change is when we remove dust, the atmosphere cools, and it gives us a downwelling anomaly and a divergence of moisture. This moisture is advected by wind to the western North Atlantic and precipitated there. So it creates a fresh water anomaly in the surface and advected by ocean currents to the deep water formation region and weakens the AMOC. For the vegetation change, the process is reversed. So the simulated mid-Holocene surface temperature is warmer than the pre-industrial in the high latitudes and cooler in the tropical region. When you remove dust, this warming signal in the North Atlantic region actually becomes weaker because of the weakening of AMOC. When we change both the dust and the vegetation, we got a very strong warming over the whole northern hemisphere, which compares better to the reconstructed temperature change. For the vegetation, it's very similar. For the precipitation, it's very similar. The vegetation effect dominates, and we got a very strong precipitation over North Africa and the Arabian region. To summarize, so the vegetation change strengthens the AMOC and causes global warming of 0.4 degrees Celsius, but dust reduction weakens the AMOC and induces a global warming of only 0.09 degrees Celsius. And if we make both changes, the effect of vegetation change dominates. So that's all. Thank you.
Thank you very much. I think we will go to the, is there a question or quick question or somebody from the audience or somebody in online while we are preparing for the next talk?
Yeah, I think we just go to the next talk.
Okay, let's do the next talk. Next flash talk. Tenzo.
My name is Zhou Peng. I'm from Beijing Normal University. My topic is response of westerly jet over the northern hemisphere to astronomical installation during the Holocene. The westerly jet in the upper troposphere, an important atmospheric circulation system, is critical for influencing global climate by changes of its north-south migration and its intensity. However, its variations during the Holocene across the Eurasia and North America are not well evaluated, which restricts our understanding of climate change in those regions. Using general circulation model experiments, here we simulate the variations of westerly jet over the past 10,000 years to show its intensity and pollution of westerly jet responding to astronomical installation. Our results suggest that the summer westerly jet gradually migrates southward and straightens over the Central Asia, Japan, and North America from the earlier Holocene to late Holocene. Meanwhile, the pollutions of the winter westerly jet barely move and its intensity slightly change. Those seasonally asymmetric changes can be attributed to the temperature structure, in which the surface length and seasonal heat flux both contribute. Thanks. My name is Zhou Peng. I'm from Beijing Normal University.
Thank you. Is there some questions? Quick questions or comments? So, shall we go to the next talk?
The westerly jet is an important component of atmospheric circulation. However, the response of westerly jet over Asia during the last glacial maximum is still not clear. Using general circulation model CAN4, we did 2 experiments, aiming at the last glacial maximum and the present day. First, the vertical profile of zonal mean westerly wind along Central Asia and Japan are examined. In these 2 regions, the westerly jet is featured by weaker and northward in summer, but stronger and southward in winter, in both last glacial maximum and the present day. But the intensity of westerly jet shows prominent differences between these 2 periods. Besides this, the position of westerly jet in these 2 regions during the last glacial maximum also differs from present day, especially in summer. The position of the westerly jet during the last glacial maximum is southward than that in present day. We found that during the last glacial maximum in summer, the heating center over the Tibetan Plateau is stronger than that in present day, and the cooling center over the Tibetan Plateau in winter is also enhanced when during the last glacial maximum. The enhanced Tibetan Plateau thermal center during the last glacial maximum is held responsible for the anomalous behaviors of westerly jet. A heat budget decomposition suggests that the reduction of adiabatic effect over Tibetan Plateau plays an important role in the abnormal Tibetan Plateau thermal center during the last glacial maximum. And thanks.
Thank you very much. I have problems with the acoustic, but okay, there are posters. Yes, we can look at posters. So yes, let's go to the next, Jian Zhu.
So can I share my screen? Okay. So this talk is about the relationship between the LGM global cooling and the equilibrium climate sensitivity. As Steve has pointed out, that LGM provides the best constraint for climate sensitivity. So this is very important. So in the past, people have tried to reconstruct the LGM global cooling and estimate the climate forcing and to estimate the climate sensitivity. In this study, I'm going to use CSM 1.2 to ask how do we actually quantify the LGM climate forcing and importantly, the effectiveness of the forcing, and how the different ocean dynamics between paleo simulation and future simulations could impact the calculation. So it has been a challenge in the paleoclimate community for several decades that how do we actually quantify the radiative forcing from land ice sheets, because the land ice sheets can impact surface temperature from multiple pathways through albedo change, impact circulation, and also the definition of surface differ between the two configurations. And one largely overlooked factor is the effectiveness of this LGM climate forcing. So here I adopted the Sherwood framework using the concept of effective radiative forcing and with adjustments. And the results are here. So basically I perform these Hansen experiments, and then I perform additional slab ocean simulation and correct the land surface temperature change. By the way, the efficacy of the land ice sheet forcing is higher than 1. This has something to do with the shift of the jet stream and the cloud systems. Within CSM2, this perfect model scenario, we can calculate everything. The ECS in the model, we know that's the truth, and the LGM cooling, and the effective forcing for everything, the efficacy. When you plug everything, those numbers into this equation, you get a big overestimation. So the calculated ECS is 4.5, so much higher than the truth in the model. What is going on? It turns out that a large part of this LGM cooling can be attributed to ocean dynamics. The bottom figure shows the LGM cooling between the fully coupled simulation and that in the slab ocean simulation. You can see that the ocean dynamics can couple with the Southern Ocean sea ice and maybe the cloud processes over the lower latitudes to amplify the cooling. So a large part is caused by ocean dynamics. When you try to account for this ocean dynamic feedback in your calculation, then you get a result that agree much better with the truth in the model. Although this is a perfect model scenario, but we think that this results emphasize the importance of a complete quantification of the climate forcing that should be consistent with the framework of forcing feedback and also the importance of ocean dynamics. That's all.
Thank you very much. I think we will keep the questions for the discussion time after flash talks. So let's go to the next talk. Xiaoyi Shi.
Hi everyone. My name is Xiaoyi. I come from Zhejiang Normal University, our study motivation is water isotopic compensations are sensitive to simulated climate and also to be the representation of physical processes in convection and cloud parameterization. They are likely to contribute to modal biases and intermodal spread in simulated isotopic compensation. Here, my topic is what are the skills of GCMs to simulate the seasonal cycle in water isotopic compensation in the Tibetan Plateau region, and if there are modal biases, do they reflect biases in the climate or in the representation of the water isotopes? Firstly, we compared the difference between the SWIM2 simulations and the observations. As you can see, we can find that the SWIM2 models can capture the spatial patterns of the precipitation, wind field, and the precipitation dirt 18 in the Tibetan Plateau. But there exists a significant intermodal spread and systematic biases. Second, in order to explain the intermodal spread and systematic biases, we divided our study area into 3 parts. From these figures, we can find that the spread of upstream precipitation in the southern Tibetan Plateau and the large-scale circulation in the northern Tibetan Plateau dominate the spread in isotopes of precipitation. And we can also find the latitude of transition from the southern to the northern region is controlled by the extent of the monsoon precipitation. Based on the results, we will further explore what's the consequence of model biases on the paleoclimate simulations. That's all. Thank you.
Thank you very much. Okay, next please. Ryota Oishi.
Okay, could you show my slide on the screen?
Okay, I'm sorry.
Or may I show my desktop?
We haven't seen anything yet. So how about we show it here and you give a talk? Hello, can you hear me? Yeah, okay, I think we see your screen now.
Can you see my slide?
Yes.
Yes,
yeah.
go ahead, Ryota.
Okay, so I'll start. Yes, I'm Ryota Oji from University of Tokyo. Today I will show you our PMIP for last interglacial simulation and related results, focusing on vegetation change. And this
we lost you here, so maybe we show the screen here and show a PPT here. So you just introduce it to us. Oh. 等一下，我们就那个。
Oishi-kun. We lost him?
Yeah, I think we lost him. Maybe we should move on, and
yeah.
After he got a stable connection, then we let him talk. Okay.
So next one is Renault Bayesian emergent constraints.
Can you hear me?
Oh, Ryota is back.
Can I share my? Can I?
Sure. Let's
wait a moment. Please.
Try it again.
Sorry, Martin.
My
Yeah, we see it now.
Can I continue? Does anyone hear me?
Yeah, Ryota, you are now.
Okay.
You can now start.
Experiment.
Yeah,
and
you can now continue.
Is, okay. Sorry for my connection trouble. We used three different version of our GCM Mirok. And the major difference among these models is treatment of vegetation. And the Mirok 4M does not include vegetation change. This is just an
We lost him again. Okay, I think we will skip Ryota and go to Martin. Sorry.
Yeah, I will share my screen. Then, yeah. Yeah, so I'm going to talk about my study of Bayesian emergent constraint, which is trying to find a statistical relationship between the tropical temperature of the last glacial maximum or the mid-Pliocene warm period and climate sensitivity in the PMIP ensemble, but also PMIP ensemble. The difference with past studies that I've done like similar stuff is that here we applied a completely Bayesian framework. So with like, I need to move that. With like a double aspect of Bayesian framework. So on the red box, you have the likelihood of the Bayesian model, which is just a very simple Bayesian linear relationship which link the tropical temperature and climate sensitivity. And the green box is just prior information you give on climate sensitivity to compute the final posterior sensitivity by also adding a proxy reconstruction of the LGM or the Pliocene. And in terms of results, so you can see on the left, we basically perform some linear regression, Bayesian linear regression in the ensemble of PMIP2, PMIP3, and PMIP4, but also PLIOMIP1 and PLIOMIP2. And in the middle column, you can see the climate sensitivity that we managed to infer thanks to the proxy reconstruction. The purple arrow gives you the estimates of climate sensitivity we got, which is all the time below 6 Kelvin. It's actually slightly better for PLIOMIP, but we consider that PLIOMIP2 is actually more uncertain than the last glacial maximum. So it's a bit difficult to tell at the moment if it's better than the estimate of the last glacial maximum. An advantage of the Bayesian method is that you can actually combine both the last glacial maximum and the mid-Pliocene warm period if you consider that both are independent evidences. And so it's very simple. You just use the posterior climate sensitivity of the last glacial maximum as the prior information on sensitivity of the mid-Pliocene warm period. And you will end up with a better constrained combined posterior, which is here in brown, and with an upper percentile of 4 Kelvin. This is still preliminary work, but I think it can be promising for the future. So if you want to know more about the methods and the different results we got, the paper is published in Climate of the Past, and you can send me an email or have a look at my poster. Thank you.
Thank you very much. So let's go and see the poster. But now next speaker. Weipen Zhang.
I don't think he's available, so we
Okay.
can move on to the next.
Sorry, yeah. Then Sarah Schaffer.
Yeah, hi. Let's... So we've simulated global biomes using CSM2 LIG 127K climate data. And we've used that as input to biome 4, which is an equilibrium biome vegetation model. The simulated biomes, which are shown on the top map, we've compared with observed vegetation data, shown as circles on that map. And we see a variety of simulated vegetation changes. One of those is simulated changes in forest biomes, shown on the bottom map, particularly expansion of forest biomes. If you look at North America and Eurasia, particularly at high latitudes, we see expansion of forest biomes, shown in green. And we also see contraction of the southern border of forest biomes, shown in tan on the maps. And in general, those changes are being driven by increases in mean temperature of the warmest month. Another vegetation change that we see is the expansion of shrubland in North Africa. So CASM2 simulates increases in the spatial extent of North African monsoon precipitation, and the response of Biome 4 is to simulate expansion of shrubland, which is shown on the map in the light brown color. And we see expansion of shrubland up and into Northwest Africa. And that sort of expansion is in agreement with some of the observed paleo data. So in overall, the simulated biomes for 127K that we have generally agree with observed biome changes. There are certainly areas of disagreement. And we also have relatively few observed vegetation records for this time period. If we were going to try and improve data model agreement, one of the things we might do is use a different type of vegetation model, such as LPJ guess. Another thing that we might try to do is to take the CASM2 climate data and interpolate it to the actual locations of the observed vegetation sample sites. And for additional information on this work, you can see the recent article by Otto Bliesner et al. In Paleoceanography and Paleoclimatology. Thank you.
Thank you very much, Sarah. Okay, so we move to Kari Morio.
Yeah, let's see, I'll share my screen here. Okay. Slideshow from the beginning. Okay, so our poster addresses the question of whether paleo temperatures could constrain projections of future warming on regional scales. And so the idea behind this is shown in the schematic diagram here on the left. This diagram has simulated paleo temperatures on the x-axis and simulated future warming on the y-axis, and each of the blue dots would be one CMIP or PMIP model. So in the case where there's a strong relationship, it could be possible to use paleo temperatures reconstructed from proxies to narrow the range of likely future warming. So what we're trying to do is to see if any strong correlations exist within the CMIP 5 PMIP 3 multi-model ensemble on a regional scale. So we're taking kind of a data mining type approach, and we're looking at combinations of the mid-Holocene and LGM experiments with various future scenarios, and looking at both seasonal and annual averages. So these maps show correlations between the LGM annual temperatures and RCP 4.5 annual temperatures on the top, and mid-Holocene JJA temperatures with RCP 4.5 JJA temperatures on the bottom. And the maps show the correlations by each grid cell. And the histograms on the right show the distribution of these Pearson's R values across all the grid cells. The curves in black and blue are the expected distribution for the R values if they're just due to chance alone. Since we're doing 15,000 correlations, we expect a certain number of them to be statistically significant just due to chance. So while the LGM R values generally follow the normal distribution, indicating that there's likely nothing too noteworthy about the correlations, the distribution of the mid-Holocene R values is strongly skewed positive. And this is surprising to us because, of course, the mid-Holocene forcing is pretty different from the future forcing, namely orbital versus greenhouse gas forcing. But the thought is that maybe similar model physics are involved in the temperature response to each of the forcings. So on our poster, we show the results of a surface energy budget calculation for Europe for the mid-Holocene JJA, which is one area of strong positive correlation. And we do make an argument that there are common physical processes at play for both time periods. So if you're interested, check out the poster. Thanks.
Thank you very much, Mario. Carrie, and okay, let's move to Alexandra.
Hi, thank you. So I will share my screen. Okay, can you see it? Okay, so I go. So hello, I am Alexandre Cocoin, and I will present you some results about water stable isotope change in PMIP type paleoclimate simulation from the fully coupled model MPI ESM VISO, so VISO for water isotopes. So and this is a work made especially in the framework of the PALMOD project. So with Martin Werner and Gerrit Lohmann at VIV. And just as a quick reminder, the water isotopes in the model, they correspond to the AV water isotopologue, so H218O and HD16O, that you implement in the same way as the standard water, except that you add some fractionation processes during each phase change of the water. And thanks to these fractionation processes, the water isotopes are a very powerful tool to reconstruct climate variation in the past, like the temperature, for example, that you can retrieve from the measured water isotopes in ice core, for example. So here, you can see the anomaly in temperature and precipitation for the mid-Holocene and the last interglacial, so 2 warm periods. Here for the mid-Holocene and pre-industrial, it's already published in the paper in Climate of the Past last year. And last interglacial are new results. And here what you can see is that we are quite consistent with the average PMIP4 model results, with, for example, warming during the summer in the northern hemisphere, as well for the mid-Holocene, or here a huge warming for the last interglacial, and enhancement of the monsoon, for example, here over Africa and over Indian region. And so, of course, all these climate variations have impact on the water isotope that are on diagnostic there. Okay, and here, so you can see still in the left-hand side, this is for the mid-Holocene, and the right-hand side for the last interglacial, and you can see a model data comparison of delta 18O anomalies, a direct model data comparison with observed data from polar ice cores, speleofilm, etc. So this is really the power of using water isotopes. You can do directly a kind of direct model data comparison instead of trying to reconstruct your temperature from some pollen data, for example. And so here you can see that the model data comparison for the mid-Holocene is quite good. We go in the same direction than the observation, except that we have a smaller amplitude. So this is what you can see. And we use here, for example, the new CSOL dataset, the version 2 that has been recently published. And here on the right-hand side, you can see for the last interglacial, so we have fewer points. So for Greenland and for Antarctica, and here 1 point for the speleofilm here. So we are broadly consistent with the observation, but here you can see that as a reminder for PMIP4, the last interglacial, we use the same ice sheet than for pre-industrial. And maybe here, this inconsistency here, maybe it means that we would need to change the ice sheet here over Antarctica. And as I said, one important point is the spatial relationship between delta 18 and temperature is the same as the temporal one. And this is what we try to analyze here for mid-Holocene and last interglacial. Here, the line here corresponds to the spatial slope between delta 18 and temperature, and that you can see that typically the temporal slope the gradient is smaller than the spatial one. So it means that your reconstruction of temperature could be influenced by this fact. And the second point is that you have also maybe a seasonal impact of seasonality. especially if you have a look with the value of for the warmer months or for the precipitation weighted temperature, you can see that we are in better, more consistent with the spatial gradient. So this is the conclusion of the paper. And so if you want to have more information, you can have a look on this paper here for mid-Holocene, or you can contact me and have a look on the poster. Thank you for your attention.
Thank you, Alexandra. Okay. Now we will go to Alexandra Koch.
Yeah, good morning. I'm just going to share my screen. Hope you can see that. Yeah, good morning or good evening, depending on where you are in the world. So what we are showing are the first results of a new biome map for the LGM using the CMIP 5, CMIP 6, PMIP 3, PMIP 4 LGM output together run through the LPJ LM FIRE model and then biomized following the Prentice-Art biomization scheme. So each LGM PMIP simulation represents one possible LGM climate state, resulting in 13 different vegetation distributions. And we show here that's the average of all vegetation distributions, and also where the climate simulate marked differences, mainly in the northern hemisphere and in the tropic savanna boundary. You can check out the poster then to see where the individual models performing better and worse, and where differences are, and also how we compare the average to the biome 18K data. We also included only 3 PMIP4 models, as these only have the output for all variables that we need for LPJ, but we're working on a way to incorporate more models from the PMIP4 effort. Here's a comparison between the 2 MIROC models and the MPI models that are in PMIP3 and PMIP4. PMIP4 here in the red box. And you can see that due to the PMIP4 models being a bit more wetter in Eurasia, we're also getting a marked increase in boreal forest in both of these models. And we will see when we have more models available whether this is a robust pattern that we see across all PMIP4 to PMIP3 models. And then because we're running at LBJ, we can also look at the terrestrial carbon cycle. And we see that the different climates sort of represent a similar picture, except that all PMIP4 models represent consistently a greater carbon stock across all latitudinal ranges. And again, once we incorporated more PMIP4 models, we will see whether this is a robust pattern that emerges there. It might be due to the increased representation of moisture. Anyway, if you want to get in touch with me, drop me an email or tweet, or leave a note on the Padlet. And thank you very much.
Thank you very much, Alexandra. Now we move to Canon Kino.
Yes, can you hear me? Oh, can you hear me?
Yes, we can.
Thanks. So, yes, so this is Canon Kino, a PhD student of the University of Tokyo. So, for the interpretation of the Antarctic ice curve, several studies for modern climate indicate that more than half of precipitation is caused by extreme events accompanied with the warm air advection from the ocean. Hence, the temperature in ice curves can have warm bias compared to annual mean. So, in this study, to understand the impact of the atmospheric conditions on the ice curves in the Antarctic ice cores, we analyzed the effect of the southern annual mode sum in LGM. As a model, Japanese stable water isotope climate model MIROC is used. While the model has already been validated in the modern climate, adaptation to polar climate LGM states is challenging. And now we've come to be able to run a model in LGM state with reasonable derivation precipitation as shown in the right top figure. So, SUM is a major mode of atmospheric internal variability of the southern hemisphere. And the positive SUM implies the strong zonal flow and brings a more larger derivation among the Antarctica in JJA, as shown in the right bottom figures. So, implying affected by the air transport from the Southern Ocean, besides cooling and less precipitation. And the variabilities of the routine at Dome Fuji in JJA are almost the same in PI and LGM. Hence, if the number of beds or the positive SUM decreases in LGM, it may contribute to warm bias. We also find that the responses of the astropes to the SUM are different between Dome F and Dome C. So please check my poster and have discussion. Thank you.
Thank you very much, Kanon. And now we will move to Hidetaka Kobayashi.
Okay, can you hear me? Okay.
Yes.
Yes.
Okay, yeah. I'm Hidetaka Kobayashi, a postdoc researcher at the University of Tokyo. My talk is about fast changes in ocean carbon cycle. Glacial interglacial variation of atmospheric CO2 is about 90 ppm. It's recognized to mainly arise from ocean carbon cycle change. Recent paleo reconstructions suggest that carbon storage in the Southern Ocean increases during glacial times. However, its contribution was difficult to be quantified, so the detailed mechanism behind this CO2 change is not clarified. So here we perform three-dimensional OGCM studies for LGM using an ocean general circulation model of MIROC. We first try to reproduce ocean property for LGM and then quantify the contribution of Southern Ocean process in atmospheric CO2. So this is a result and discussion. So we found that enhanced Southern Ocean stratification is the most important process for reproducing the glacial deep ocean with its tropical light carbon and low oxygen and old radiocarbon age consistent with paleo data. This figure shows the simulated oxygen in the original LGM case and our best LGM case. We found that deoxygenation in the deep ocean is well reproduced in this best case. Besides, the best LGM case also reproduced well the delta carbon 13 and delta carbon 14 age also. And then we found that our best LGM case shows about 80 ppm CO2 change, which is the most largest response in the complex three-dimensional OGCM studies. We divided the contributing factors, and we found that carbonate compensation is the most prominent role in the glacial changes in atmospheric CO2. So this result reported today are now preparing for submitting papers. So thank you very much.
Thank you, Hidetaka. Thank you. Okay, now we will have Rumi Ogaito.
Okay. Do you see my screen?
Yes.
Okay. I'm Rumi Ogaito.
Oh, but it's not the full screen.
Okay. Is this okay? Okay, I'm showing this. We have conducted PMIP4 experiments using MIROC ES2L. It's an Earth system model developed for CMIP6, PMIP4, and conducted 4 experiments for PMIP, LGM, last millennium, mid-Holcim, and last integration, all available on at ESGF. You can download, and the explanation of these experiments are on at GMD discussion. I don't have so much time, so I'm gonna show some results from LGM. Left-hand side panel showing a anomaly of air temperature at surface in comparison with baseline pollen reconstruction, and it shows the general agreement with proxy data with some regional discrepancies that we should look into in future. Right-hand side panel showing, because this model is Earth system model, it calculates carbon cycle. Right-hand side panel showing the anomaly of export production of ocean for LGM relative to PI in comparison with data archived by Kofel et al. And again, this
Can you click the next slide?
Excuse me?
Can you click the next slide, or is it the organizer? It's the first slide here.
Yeah, we are not controlling here.
Oh.
This. You don't
Okay.
You don't see the second slide?
Good. This
okay,
is good.
Okay. Also, you didn't see the figures, so I'm sorry, but I'm explaining the second slide and about export production. There is a good agreement with proxy data, but some regional discrepancy can be seen in the South and part of Atlantic. This may be correlated with buyers of dust emission from South America. You can see more detail at my poster discuss. Thank you.
Thank you very much, Rumi. And now I hear that the next speaker, Jujun Sun, is missing. So shall we skip and go to Rio V. Ramos?
All right. I'm just gonna share my screen. Okay. Sorry.
Yes, go ahead.
Sorry, I'm just having some technical difficulty. All right, now, okay. Yeah, hello, I'm Rio V. Ramos, and this is an overview of the work I've done with Allegra Legrand and Michael Griffiths in close collaboration with Dan Lichmore, Greg L. Sicer, Jessica Tierney, and Francesco Posada. So one of the emerging ideas in terms of the uncertainties associated with ECS estimates is that much of its intermodal spread is linked to the differences in cloud and convective parameterizations. Now, because water isotopes are sensitive to these changes in the same parameterizations, we can therefore use them as constraints for evaluating model performance and potentially diagnose model biases. So in this study, we've evaluated a suite of isotope-enabled GIS E2.1 simulations against the low-18 compilations from both speleostems and ice cores spanning the last glacial maximum, mid-Holocene, and the pre-industrial periods. Now, for the simulations part, apart from the standard GIS runs, we have also explored 4 other parameters such as rain evaporation above the cloud base, entrainment rate, cloud droplet radius, and critical cloud water content for a total of 9 different simulations. Now, so for our initial results indicate that the first order spatial pattern of the Delaunay of precipitation is in excellent agreement between proxies and in all simulations across all time periods. Now, so the left panel here shows you the spatial distribution of the Delaunay precipitation from the standard GIS runs for the pre-industrial on top, mid-Holocene in the middle, and LGM at the bottom. So the right panel, on the other hand, shows you the scatter plots between proxy and simulated Delaunay for each of these time periods. Now, if you look at the isotopic changes between LGM and pre-industrial on top of the panel and mid-Holocene and pre-industrial here at the bottom, the magnitude of the Delaunay anomalies are consistently smaller in all the simulations than those of the proxies, with the greatest offsets coming from both Greenland and Antarctica shown here in squares. Now, if we look at the scatter plots of all the parameterizations shown here in different colors versus those of the proxies, the mismatches that we've observed in the standard run remains evident. However, modifying droplet radius for the LGM and pre-industrial and critical cloud water content for the mid-Holocene minus pre-industrial changes shows an improvement from the standard run, as shown here in the final column. So these results then indicate to us that the isotopic changes in the LGM and mid-Holocene periods are differently impacted by these different sets of cloud and convective parameters, implying that fine-tuning future simulations requires determining all the possible parameter combinations. So then in the future, these best runs will be run in fully coupled mode under different climate conditions, and through data assimilation, we hope to evaluate the impact of these parameters to ECS in GIS E2.1 models. For further details, I invite you to look at our posters, and I look forward to the discussions later on. Thank you.
Thank you, Ryovie. Now we will move to Winlu Chan.
Hello, can you see my full screen, and can you hear me?
Yes, we can.
Oh, okay, all right, thank you. Good morning, I'm Winlu Chan from the University of Tokyo, and my poster is going to be about some climate simulations that were done in the context of PMIP2, as well as some recent additional experiments using MIROC 4M coupled to the OPJ dynamical vegetation model. And up to now, very few models have used dynamical vegetation within PMIP. And a small caveat here is that we keep the ice sheet extent fixed to the PMIP2 condition. So this mid-Pliocene warm period was the most recent period when atmospheric CO2 levels are thought to have been similar to present day levels. And in our experiments, we look at scenarios with the PMIP default of 400 ppm CO2 and also 50 ppm above and below. With dynamical vegetation, we see that shrubs, bare ground and desert occupy a much larger area across North Africa and also Southwest Asia in comparison to the fixed vegetation based on the PRISM data. And boreal forests occupy a larger area across Greenland, but these forests themselves are partially replaced by grassland in southern Siberia, especially as the CO2 increases. Right. In general, we see less warming with dynamical vegetation, in particular at the higher CO2 values, and also in the Northern Hemisphere. But on the other hand, at 350 ppm CO2, there's actually slightly more warming in the Arctic region, except across Greenland and the northern coastal areas of Canada. And this corresponds to the regions where tundra is replaced by bare ground or boreal forests. And another important aspect of our work is reconciliation between model and proxy data. Now, this is still ongoing, but here I've compared the SST anomalies with Alkanone proxy data from the Turnier et al. 2019 paper. Pacific SST anomalies are slightly smaller when we use dynamical vegetation. And one consequence of this is that there is a slightly better match with the proxy data at higher CO2 values. Thank you very much for listening.
Thank you, Winley. We will now move to Ning Tan. Ning?
Hello, everyone. Can you hear me?
Yes.
I'm sharing my screen. Can you see my PowerPoint?
Yes, but it's not on the full screen.
Okay.
Yeah.
Now I think it's okay. Yeah, hello everyone. I'm Ning Tan. My report is about our modeling work on the mid-Pliocene. The mid-Pleistocene warm period around 3 million years ago is the most recent geological epoch with present-like atmospheric CO2. And so the climate is estimated to be warmer than present by 2 to 3 degrees and with strong warming amplification at high latitudes. Thus, with a large land ice melting over both polar regions. And relative to PMIP1, PMIP2 selected a specific interglacial period named MISCAM5C, where the orbital parameters is similar to the present. Thus, to explore the climate of MISCAM5C and update boundary conditions, and to discuss the climate responses to different forcings during this warm period, we carried out a set of experiments with French IPSL AOGCMs, CM5A and the fast version CM5A2, according to the PMIP2 protocol, and experiment design is also according to the PMIP2 protocols. Relative to PMIP1, the major changes on the land sea mask in local grid is shown here, and is for the closure of the high latitude seaways. So our results show that the simulated PMIP2 climate presents enhanced warming, the red curves, relative to the PMIP1 conditions. This results from the enhanced Atlantic meridional overturning circulation caused by the high latitude seaway changes. The sensitivity experiments show that apart from the high level CO2 concentration, shown with the green curves here, the modified orography and both the reduced ice sheet over both polar regions has a strong contributions on the warming at mid to high latitudes. And when compared to the data, the PMIP2 simulated SST is more consistent with the reconstructed data relative to the PMIP1, but the modeling still underestimates the strong warming that recorded in the data larger than 4 degrees. So that's all. More details about this study can be found in our published paper in Climate of the Past, and as well as the posters. Thank you.
Thank you very much, Ning. Okay, let's move to Ranpen.
Screen sharing. Ning, can you stop screen sharing so I can share my?
Okay.
Thank you. Right. Can people see? Okay, great. Hello, everyone. I would like to introduce.
Screen, sorry. Can you put it on full screen? We see two slides at the same time.
Let's see if I can fix it.
Or if you want to continue this way, so it's fine.
I'll just continue this way. I'm worried to make it even worse. All right. Yeah, hello everyone. I would like to briefly introduce our recent results on increased climate response and Earth system sensitivity from CCSM4 to CESM1 in our mid-period transient simulations. So the motivation of this work is really trying to understand how can paleo observations help assess the overall model performances across generations with the ultimate goal of help model development. So for this work, we focused on 3 generations of Earth system model family, the CCSM4 model, CESM1, and CESM2. So CESM2 is the CMIP6 model, and CCSM4 was the CMIP5 model. So for this poster, I want to address 2 questions. So first one is, what information can we extract from paleo observational SSTs to help distinguish and evaluate the overall model performances across generations? And the second question is, what are the features of improvements or degradations between the generations of CCSM and CESM in terms of simulating the mid-period transient climate? I want to show some of the key results that we discovered through analyzing those simulations and comparing them with the proxy data. So on the to the left, I'm showing a comparison between the proxy warming structure, which is captured by this polynomial fit of proxy data, and compared with the simulated meridional warming structure of sea surface temperature by 3 generations of models. And as you can clearly see, clearly make the assessment that overall CESM1, which is in the middle, is better than CESM2, and both of which are clearly better than CCSM4, which is showing left here. And to the right, I'm showing a figure of regression of global mean surface temperature as a function of main SSTs at the proxy sites. This regression is done for all of our simulations, and looks like, based on this really good linear regression, the proxy SSTs do have enough information to provide a assessment for simulated global mean temperature by those 3 models. And based on this assessment, we can clearly see that the global mean surface temperature by CESM2 is higher than CESM1, higher than CCSM4. Given that they're running with the exact same boundary conditions, we can also make a assessment that the Earth system sensitivity beyond the equilibrium climate sensitivity is the highest in CESM2, and it's higher than CESM1, and then higher than CCSM4. And if we plot the estimated model SST on this regression, we can immediately start to see that CCSM4 is probably too cold. Their system sensitivity is potentially too low. And in contrast, CESM2 is potentially too warm, and our system sensitivity is potentially too high. Right. I'm trying to advance. Right. Yeah, so the last discovery we find by running those simulations is that tropical responses are very different between those models. especially between CCSM4 and both CESMs. So both CESMs shows a El Nino-like tropical climate response with weakened water circulation, weakened equatorial upwelling, and strong warming in the eastern equatorial Pacific compared to the western equatorial Pacific, which is not the case in CCSM4. Right, if you're interested in any of those results, feel free to check our posters. We also published those results in a recent James paper. And we're also releasing the data. So if you're interested in analyzing in depth any of those model discrepancies or doing fancier model data comparison, please give us an email. We can direct you where to find the data. Right, thank you.
Okay, thank you very much, Ran. Okay. Now we will go to Taro Higuchi, even a deeper time.
Can you see my poster? And can you hear me?
Yes.
Okay, nice to meet you. So I'm Taro Higuchi. So I'm a PhD student from the University of Tokyo. So the water cycle change in the East Asia due to future global warming is attracting a lot of attention. The DCM simulation predicted annual precipitation in East Asia will increase due to global warming and leading to more humid conditions. On the other hand, Cretaceous terrestrial proxy data indicated an acidification in the East Asia during the mid-Cretaceous when the CO2 level was especially higher and the climate was warmer compared to early and late Cretaceous. However, it looks contradictory from global warming predictions. So therefore, to examine why the water cycle response in the East Asia to increasing CO2 differs between present day and the Cretaceous. So we performed a CO2 sensitivity experiment with present day and Cretaceous geographic condition using LOGCM MILC4M. These figures shows the annual precipitation change due to increasing CO2 on the present day and the Cretaceous geographic conditions. So first, the annual precipitation change in Cretaceous experiment is consistent with the water cycle change during the mid-Cretaceous. So additionally, you can see the opposing response in the East Asia water cycle to climate warming. In the present day, the precipitation in the East Asia increased due to warming, while it decreased in the Cretaceous. So we speculated that the different water cycle response in the East Asia are attributed to presence or absence of the Tibetan Plateau. So conclusively, this study highlights that the Asian local water cycle change due to climate warming is strongly dependent on geographic conditions, including the Tibetan Plateau. So in our poster, we are also compared the results showing now additionally with the Pliocene and Eocene experiments. Please see the poster for detail and leave any comments or questions. Thank you.
Thank you, Taro. So now we will go to Wenmin Man.
Hello everyone, my name is Wenmin Ma. I come from IIT. My topic today is potential influences of volcanic eruptions on future global monsoon precipitation changes. The robust post-eruption signals including the temperature, the precipitation, the monsoon circulation responses, and also the interactions between the energy and the water cycles, raise the question of their potential for a role in future climate. However, the major volcanic eruptions are generally not included in current climate projections because they are unpredictable events. In a recent study by Baker 2017, 60 sets of plausible future volcanic forcings were derived from the reconstructed volcanic activity of the past 2,500 years. We conduct 60-member 21st ensemble simulations use this stochastic volcanic forcing with no ESM under the RCP 4.5 scenarios. For comparisons, we also conduct 60-member zero volcanic forcing ensemble simulations and also 60-member the constant background volcanic forcing simulations. This figures shows the precipitation difference between the volcanic forcing and non-volcanic forcing scenarios over the global land monsoon domain. The ensemble spread with the realistic eruptions increased by about 20% compared to the non-volcanic and the constant background volcanic scenarios. And compared with no volcanic forcing scenario, the global monsoon precipitation shows about 10% overall reduction in the volcanic forcing scenario, and regionally, Asia is the most impacted. The time of emergence, which is defined as the mean time at which the changes of global land monsoon precipitation emerging from the internal climate variability, is delayed over a large part of the global land monsoon domain in the volcanic forcing scenarios, and volcanic activities could delay the DOE of anthropogenic inflows by about 5 years and over about 60% of the global land monsoon area. That's all my talk. Thank you.
Thank you very much. Wenmin, and then now we go to Feng Du.
Yeah, I have a pre-recording. Can you see this?
Hi, Fon.
We don't hear anything.
We don't hear anything.
Oh, so.
Should we play the video we have here? Fon? So okay, so
can you hear me?
So we.
Hello, everyone.
Okay.
Can you hear? Can you hear it now?
Yes.
Okay. Sorry.
Hello, everyone. Our study attempts to resolve a long-standing model process discrepancy regarding the temperature response to volcanism. Previous studies, the IPCC AR5 report, for instance, have identified the disagreements between paleoclimate reconstructions and climate model simulations with respect to the magnitude and recovery from volcanic cooling, as well as the peak cooling year, questioning the fidelity of climate model simulations, reconstructions, or both. Using the paleo data simulation framework of the last millennium reanalysis, we first reproduce the discrepancy we see in the IPCC report and find noteworthy different impacts from the trillion waste records, denoted as TRW, and the density records, denoted as MXD. After which, we investigate the question, what accounts for the discrepancy? Following previous studies, we identify and confirm three main causes with respect to trillion data. The first is limited spatial coverage. Both trillion width and density networks are sparse. Second is the seasonal bias. Since trees register climate only during their growing season, annual temperature is not their best target for reconstruction. And third, biological memory issue. Trillion width has significantly larger lag-1 autocorrelation than density data, which leads to the lag in response to temperature directly. So what can we do about them? Well, we can assimilate the density data without trillion width data to alleviate the biological memory issue. We can reconstruct the northern hemisphere summer temperature instead of annual temperature to suppress the seasonal bias. We can perform the analysis at proxy locations only instead of the globe to account for limited coverage. Yes, we can, and so we did. And boom, we get this. The problem seems solved, yet more density records would be great. Thank you.
Thank you very much. It's good. And then Patrick? No. Qingwen, sorry.
Hi everyone, I'm Qingwen from Nanjing Normal University. My poster is about the role of the Tibetan plateau in the formation of Pacific meridional Tarling circulation. In modern climate, it is well known that there is a strong AMOC in Atlantic Basin, but there is no PMOC. This phenomenon is established around 10 million years ago. Also in this time, there is a strong uplift of Tibetan plateau. So the potential role of the uplift of this mountain on the PMOC is investigated by using the CESM model with and without this mountain. The results show that after we're removing this mountain, there is a strong PMOC established, but the AMOC is shut down. The mechanism shows that after we removing this mountain, it will generate Rossby waves in North Hemisphere with anomalous high pressure system and the water vapor divergence over Western Pacific. This will increases the surface salinity. So the surface salty water transport northward and eastward along the Croatia extension and further downward along 26.8 isopiclos and further southward to form the PMOC. This path is determined by the ocean potential vorticity. So our work changed the traditional view that the Bering Strait or Rocky Mountains is the key factors for generate Atlantic and Pacific seesaw phenomena. So for further details, please see our papers. Thank you.
Thank you very much. And now we will have the final flash talk from Patrick Bartlein.
Hi, this is about the calendar effect and the need to adjust it. And this is based on work I've been doing with Sarah Schaefer. The calendar effect arises from summarizing model output using a modern day calendar. We know that the length of the months change over time, and consequently, if you use the modern day definition of the calendar, you wind up comparing data that originated at different parts of the Earth's orbit. The problem is that the calendar effect shown in the panel here can impart things that look like interpretable anomalies. So you can see interhemispheric contrasts, land-ocean contrasts, all sorts of things. In extreme cases, this is for a last interglacial simulation, it can actually switch the sign of the long-term mean differences. So here's long-term mean differences adjusted for the calendar effect, not adjusted. And if you look at North America and Asia there, you can see that, in fact, for October, November, and into December, the signs of the anomalies are switched. So we've been doing a few things to further elaborate the program we produced. One is to compare several other different ways of doing the pseudo-daily interpolation that's necessary for making the adjustment. Pseudo-daily interpolation of temperature is not really an issue, But for precipitation, here for a Mediterranean type precipitation regime, this is modern daily data, it can make a difference. The thing is, the several different ways of doing the interpolation really don't differ much from one another at all. So here they're just kind of plotted on top of one another, and you can't really tell much of a difference. Another issue that has arisen is whether or not it would be better to use archived daily data as opposed to pseudo-daily interpolated data. And in fact, it always would be, because there are a lot of things you could do with daily data, except it does take a lot of space. On the poster, this panel shows the long-term mean differences in the left-hand column for temperature, and the calendar effect in the right, and then same thing for precipitation. And you can look at the PDF and blow it up and get a better idea that I can show you here. But here's the biases between using archived daily data and using pseudo-daily interpolated data. And these are the adjusted long-term means. If we kind of blow those up, take a look at them, the biases are very, very small. You really have to hunt for just a few grid squares in various places where there's any kind of noticeable effect at all. This is precipitation rate, millimeters per day. Most of the map is in the bottom two color categories, indicating the bias is less than about a quarter, 0.25 millimeters per day at a maximum. Now, if you actually look at time series of, in this case, monthly averages of the pseudo-daily interpolated data or the archived actual daily data, you can see some slight differences. What I did here was to plot the calendar adjusted daily input underneath in red, and that based on pseudo-daily input on top in black. And so when you see red showing through, that indicates there's a difference. In the case of temperature, you can't really see any at all. In the case of precipitation, there are a few points that do kind of emerge. On the bottom here are scatter diagrams between the calendar adjusted daily data and the pseudo daily data. The line is a one-to-one line, not a regression line. So to essentially take a message away from this is precipitation biases are small, temperature biases aren't really noticeable at all, and there's really no practical influence on the interpretation of long-term mean differences or on the calendar effect itself between using archived daily data and using pseudo-daily interpolated data based on archived monthly data. That's it.
Thank you very much, Pat. Now we have all the flash talk in this morning session, and I think we can have some questions or discussion for the next 15 minutes. Are you okay without break? Is it okay?
Yeah, maybe that's okay, or maybe we can also move to the discussion session after the break. So we have a short announcement to make for the activities to follow because it's delayed a lot.
Okay, go ahead.
And there were not so many people turning up yesterday in the parallel discussion sessions. So we have decided to unite all three parallel sessions into one. And also shorten the discussion to half an hour. So we will start from 10:30 and to 11 in Beijing time. I'm not sure what time it is for other people. So is that okay? So no, we will take a 10-minute break, but if people want to ask questions or discuss something, probably you can continue.
So it means that we will stay in the same room and everybody will be in the discussion?
Yes.
Okay, after this break, 10 minutes break.
Yeah, but I think people can continue to discuss during the break.
Okay. Is there some announcement or something from Pascal before this break?
No. Hello, everybody. So, no, thank you. It's a very nice session, lots of nice talks. So I invite people to comment on the ballet and also comment for the discussion. And I hope we have a good discussion after the break. There are lots of questions on this topic. So, yes, thank you.
Okay. So let's see each other after 10 minutes break. Okay.
Okay.
Okay, hello.
Hello.
Hello. I just wrote in the chat that maybe people can use the Padlet, and now we can do some discussion or questions for the next 30 minutes.
我还是静音了吗？那个我这里显示的好像是静音，是不是？没有的啊，但那个窗口显示静音。
Hello.
对，没关系。Yeah, hi. So we welcome anybody who has questions about the sessions or talks. But Professor Abauchi, you are in charge, so.
It's okay.
Probably
Yeah.
have a lot more questions.
Well, I tried to say that yes, we have a session on climate sensitivity, and we now learn that a lot of feedbacks are working, so we can talk about both aspects of the climate sensitivity and the feedback. So, shall we start from the proxy problem we had? Are there people who like to talk about or ask about the questions on proxy model intercomparison? For example, the proxy, LGM proxy, we have now new data, and we were asking ourselves that there are several data sets. So now what was changed, or where do we have to be careful with? Or there are many questions on the feedbacks, I think. Also, we had this question on the high sensitivity models. Or now we have quite a range of climate sensitivity of GCM. So we heard that, for example, CESM is now compared with the CCSM, and I think they learned a lot with the high and low sensitivity model. So.
So we have one question here. Can you come up to stage? Oh.
Okay, I'm just curious about because I always found that the proxy data always overestimate maybe compare the climate compared to the model data. So it's about it's due to the climate problem or the proxy problem. Yeah, that's just I always found that problem. Yeah, that's it.
Is there any expert on proxy reconstructions here? Let's see. Yeah, probably those people are in Europe.
Yeah, or the team of Jessica. Yeah, we are missing those people. Maybe Pat Bartline can help us.
I'm having some internet trouble, so I didn't quite hear the question. It seems to be resolved.
Can you come up and repeat your question here?
Yeah, can the speaker switch on the video? Can you switch on the video and speak?
Hi. Yeah, I will repeat my problem. Oh, okay, so I always noted the proxy data compared to the model data, they always have the overestimate the results. Yeah, and so I'm not sure it's the a problem of the model or the problem of the proxy data. So because the difference is a lot, especially for the temperature or the precipitation. Yeah.
Well, there are some sort of mechanical statistical issues that come up in doing regression type reconstructions, and there are a lot of methods that are related to regression type approaches. In that, if you imagine a scatter diagram, the regression line never can be as steep as the overall slope you wind up seeing. One solution is to switch to a method called weighted averaging partial least squares, which is a technique that adopts a model that suggests that an individual, say, pollen type or diatom or something, has a unimodal response to climate. Long story short is that it's possible to modify that approach to reduce that tendency for regression reconstructions to underestimate at the high end or overestimate at the low end. There was a paper in I think quaternary research recently on that. Sandy Harrison has some students working on that topic, and I think there may be a paper later that will probably go into it. Can't find it right now, but yeah, there are some things that we still can do better as far as making reconstructions that could at least remove some of the mechanical differences between reconstructions and simulations.
Okay, thanks.
Thank you very much. Other questions? Sam Sheriff Tadano, you are writing in the chat. Can you repeat, Sam?
Hello, can you hear me?
Hello. Switch on your camera.
Okay. Hello. I was interested by the comment by Jian in the flash talk, and yeah, so we use the data from the LGM to estimate the climate sensitivity, and in doing so, we have to remove the effect of the surface cooling by the glacial ice sheet, and we can calculate the strength of the ice sheet induced cooling using general circulation models, but each model can show a different strength, different magnitude. Like, for example, if we have a -6 degree global cooling, and some model can show a 2 degree cooling by the glacial ice sheet, or other models can have a 1 degree or 3 degree cooling by the glacial ice sheet. And that can have a large impact on the equilibrium climate sensitivity. And I was wondering if we can use modern observation over the Antarctic or Greenland ice sheet temperature to constrain the magnitude of the glacial ice sheet induced global cooling. And what do you think?
Jian, do you like to respond?
Yeah. So thanks for the question. I think it's interesting. And I want to add more uncertainties on top of your question. So it's not just the like a drag effect or mechanical effect of the ice sheets. We also have basic understanding, like a gap about the albedo. What's the albedo of glaciers? Those, I think that's more basic. And if you check the models, they still, I think they differ in the prescribed albedo. That's another uncertainty. And also this is coupled if process with cloud. So if you have this jet stream shift, say southward, and if the clouds moves together with this jet stream, then the clouds is moving southward towards the equator, which can block more solar insolation. That's a positive feedback. So it's really complicated and it's hard to do. And we really need to examine details using all the available information we can get, including using multiple models, doing better observations, looking carefully at the present day information.
Okay, thank you.
Thank you.
Can I say something on that, Ayako?
Yeah.
Because it gets back to a point I made in my talk, which is that I think if you're going to follow the framework that we use for modern climate, you wouldn't be trying to remove the cooling caused by something like an ice sheet. You'd be trying to estimate the watts per meter squared that the ice sheet that is caused by having the ice sheet there, because the amount of cooling from the ice sheet depends on the sensitivity, which is the thing you're trying to estimate. So you're uncoupling a coupled problem by thinking about it that way. It may not affect the answer so much, but I'll just throw that out there that if possible, I think it might be preferable to think of these things in terms of watts rather than degrees Kelvin.
So related to Steve's comment, Masa Yoshimori and myself, we tried once to do a feedback analysis. So I think the try to look at the feedback for each model and watt per square meters, and that would maybe be a hint for this kind of study. Is it helpful, Jian? Yeah, Steve, thank you. Okay, and Pascal, you have an exclamation mark in the chat box.
Yeah, so maybe it was another point, but to go on this line with the estimates, it's when I remember when I did that for the LGM, I had the problem of what we do with the ice sheet, because we can estimate the forcing with albedo by using the albedo of the model or whatsoever, and look at the differences between models. But we also have to take into account the fact that we impose an ice sheet. So we impose a lapse rate, and this you don't know how to estimate it properly in practice. And the way you estimate, you can get different numbers. I know that. So that's also how do we do that. And we also know that when you run your simulation, you have to redistribute the mass. And the same, the way you do it, you change the mean levels in your simulations. And how do we account for that? Are we really able to do it properly? And is there someone with a way to do it? I would say, I would ask.
Yeah, somebody can respond to Pascal?
I'll just ask a question. Do you always make sure that when you put in this big ice sheet that the mean sea level pressure rises accordingly? In other words, that the atmospheric mass is conserved?
Normally, yes, but it might be done differently in different groups. And I know from I didn't check this around, Masa is doing that, but I didn't look at the new models, but sometimes it's not exactly done. It's unclear to me, to be honest. I'm not sure from the output. Maybe with all the outputs we could do it. So I don't know if other people have done that already and look at this point, but I remember it was a big point for me, as was the point that you have emerging lands and you need to estimate the albedo effect or the land effect on that. And you can do it different ways and you end up with slightly different numbers. But since it's all small errors, when you add that to estimate the sensitivity for the different feedbacks, that it can make a big error bar at the end.
Yeah, I think I have a look at the NCAR models before. When you put an ice sheet in, the sea level pressure increases accordingly, and also the pressure broadening effect of CO2 is actually quite significant.
Okay, Masakazu Yoshimori, I think you have some related question or comment.
Yes, a kind of maybe comment. I'm just wondering it's not directly related to what have been discussed, but whenever I do some kind of feedback analysis, I always want to know what's the difference in radiative forcing between models. And I wonder if it's too much to ask to think about somehow estimate radiative forcing, say running the AGCM with fixed SST for parallel climate simulations, or I'm wondering if there was such kind of discussions before, or the status of the community's feeling about the providing the radiative forcing data.
So there's not only the uncertainty in the climate feedback, but you are talking about the radiative forcing.
Right.
For example, LGM ice sheet is counted as a counted in one component of radiative forcing.
Right. Also the greenhouse gas as well.
Yes. Yes. Can someone join in this discussion on radiative forcing or uncertainty on radiative forcing?
I can just point out that we have the same problem in CMIP 5 for the historical forcings, and now there's an RF MIP to try to fix that. So maybe we need a PRF MIP.
Yeah, okay, PRF MIP.
So
yeah, so I would like, oh, sorry, go on.
Yeah.
Looks like we skipped a question from Meng Zuo here. So she had a question in the chat box.
Oh, sorry.
So can anybody respond to that?
Yeah, hello. So the question is about our study that, so in our study, we mentioned 3 points to reconcile the temperature response to volcanic eruptions in model simulations and our reconstruction. And we are assuming that the response in model simulations are correct. So the question is, so it's known that the models, some models are overestimate the temperature response to volcanism. So what do I think? So that's a very good point, I think. And so the eruption events we considered in our study, which I didn't show in the poster, are at similar size compared to Pinatubo. So which is actually the reference for the aerosol microfluidics parameterization scheme in the PMIP models. So that in that case, models are doing well in estimating the temperature response. However, we do observe that significant mismatch between model simulations and our reconstructions for extreme large events like Summerlands and Tambora. So for those events, we do think there are some room for models to improve. So that's it. Thank you.
Thank you. Thanks for your answer. And I have a further question about the last millennium reanalysis dataset. Yes, in recent years, I have found that there are a lot of last millennium reanalysis output based on different model simulations. And I think there is certain uncertainty between different last millennium reanalysis product. So I don't know how to better use the reanalysis data for such as for me, I focused on the climate response to volcanic eruptions. I have make an analysis over the China region, but I found that the reconstructions and the last millennium reanalysis the results is so different. So I don't know how to understand the different results. It's about the model simulation or uncertainty in proxies.
So you mean you see mismatch between model simulations and the last millennial analysis over the China region?
Yeah.
Yes,
I don't. For the reconstructions, last millennium reanalysis, and model simulations, I don't know which is true. Yes.
Okay, I see. So for the China region, the last millennial reanalysis is mainly based on trillion records, and we, like in our study, we've seen that the trillion records have several problems regarding capturing the volcanic signal. Like they are seasonal process, so they cannot register the annual temperature very well. So in the official LMR reanalysis product, it's an annual temperature reconstruction product. So there might be some seasonal bias effect, degrading the quality of the reconstruction. So for specific scientific questions like volcanic, like the response to volcanism, we do need a specific reanalysis. So the official reanalysis may not fit your question well.
Thank you.
Okay, thank you. Now we had good discussion on volcano, and there are some questions or discussion on ocean. Hutan, you are asking question, and also Jian-Tzu, you are also commenting on that. Can you discuss in a bit detail?
Yeah, I think I basically agree what Steve just said. So the ocean dynamics effect is through changing the fast feedbacks like sea ice, albedo feedback, and cloud feedback. So in CSM, I have found that for LGM, the ocean dynamics is very different, and that can couple with the sea ice, and then the sea ice brine rejection will enhance this deep ocean formation. So there's a coupling there, and which promotes the sea ice expansion. As a result, in the LGM simulation, the albedo feedback could be as big as, say, 0.6. And if you compare that in 4 times CO2 experiments, the number might be 0.3. So there's a big difference in the fast feedback, but the root cause is the coupling with ocean dynamics.
Okay. Also, Jian, related to Hutan's question, you presented 2 versions, but the AMOC, was the AMOC stronger at LGM than pre-industrial, and how is the AMOC affecting the climate sensitivity?
Yeah, AMOC do impact the regional temperature, and you can see that. I think based on some previous studies that, first in the LGM simulation, we have a shallower AMOC, maybe slightly stronger, I cannot recall the detail. And there's also maybe southward shift of the convection center because of the sea ice expansion. And this will impact the lower troposphere stability in the atmosphere, and that will modulate the cloud feedback. And you also have this sea ice feedback. So the AMOC do make a difference. But overall, it's smaller than that from the Southern Ocean dynamics.
Okay. Well, I thought the AMOC could affect the Southern Ocean through bipolar seesaw, and that makes a difference whether AMOC is on and off.
Okay. Yeah.
Okay, so there are several points to discuss on that, but okay. Betty has a question. How can we get the best estimates of global mean temperatures from proxies? Betty?
I can just add there. That would be a question that Dan Lunt would have asked too. And I keep asking myself, because even if you just go to the last interglacial, 125,000 years ago, there are very few terrestrial records. And so we have marine records, and we're trying to take those and come up with a global mean temperature, which we want for climate sensitivity. And so if you go even farther back, it's even more of a challenge. So it'd be interesting to hear from the proxy people or the data assimilation people, how we could do this better and get good uncertainty intervals for that.
So again, are there proxy people?
And maybe they're all in the next session. I don't know.
It's kind of a statistics question in a way, isn't it? If you can quantify the uncertainty of all your data points, then you just need a model to fill in the blanks. You could use an ensemble of model simulations and find the one that fits the data best and adjust it to match the data. That would at least take care of things like the land-ocean temperature bias, which is probably significant and is probably captured reasonably well by all the models. But it might not be captured if you just take a simple-minded average of all the data points without thinking about whether they're land or ocean data points, just for example.
Pat Bartline?
Yeah, I'll bite on this question too, because I've talked to Betty about this before. But yeah, I think it should be something between a straight reconstruction-based thing that's somehow assisted by a model. But the problem is that if there's bias in either one of those two data sources, you could comfortably converge to agreement that doesn't actually exist. So I think we're headed in that direction. One problem with assimilation type things is that if, say, you're given a suite of climate model simulations and you pick the best one, or the one that matches the data the best, there's the possibility of creating a Frankenclimate where temperature comes from one model, precipitation comes from another one, and you then lose the nice thing about model output, which is the physical consistency among the variables. That's something that's hard to do with inverse modeling in the climate reconstruction sense, because typically individual variables are reconstructed one at a time. Some approaches, like the old canonical correlation approach of Webb and Bryson in the 1970s, does kind of mediate that a little bit, and the modern analog approach does as well. But it's possible in doing just data-based reconstructions or paleo evidence type reconstructions to get reconstructions of climate variables that are no longer physically consistent. So I think when we do this, which we will at some point, it's going to take a balance between knowing all the paleo data as well as selecting the model output in an appropriate way.
So related to that topic, do you have any opinion about the talk given this morning? He used the Bayesian constraint. I don't fully understand the paper, but he got an LGM temperature decrease only about 3 degrees Celsius, which seems to be much lower than we have been talking about during the past 2 days.
Well, I don't have an opinion on that, but it seems kind of typical in that because there is this tendency for statistical approaches to underestimate the extremes. The paper I referred to earlier is I put it in the chat. It's coming up later today, I guess. Lu Mingming, it'll be at 16:04 China time. So that's describes some of the work that they're doing in Reading and in London. It's not a hopeless task, but it's still one that we need to think about more.
If you're talking about the Renou et al. Paper with Bayesian LGM, it was the tropical temperatures that you're thinking about, not global mean.
Okay. So the global mean is larger than that?
At least the one I'm looking at.
Yeah, for the last interglacial, for example, they may only have marine temperatures and mainly over the Atlantic Ocean, and yet try to come up with a global temperature, and it's challenging, to say the least. And I'm not sure I believe what they've come up with because of that when I look at a model. So I think you're right. I think you have to combine models and data to somehow do this well. But there are challenges with that also.
I guess the thing that that makes me confident that this is possible to do is the studies that we and others have done, just looking at things like the large-scale patterns, land, ocean contrasts, high latitude versus low latitude, and in fact, the models are, and the data are consistent across a range of different climates. Of course, we don't have data for future climates, but when you plot things like land-ocean contrast, they basically plot along a straight line from the LGM all the way to the Pliocene and to doubled CO2 and 4 times CO2 and so on. Because the data and the models agree on those large-scale patterns, that suggests that those patterns are real. They're not just a artifact of the model, or they're not just something that the data can't help but reconstruct, but in fact, it's probably something real in the climate system. So I think that supports the idea of trying to do more, and in particular, starting to get more focused regional reconstructions and comparisons. The overall global temperature number is interesting, but to me it's just a number, and the real consequences of the climate of the future, as well as what past climates have done, are much more regional in their expression.
Okay, I think we are running out of time, but I think Martin Renault, you are making a point responding to several people. Martin, can you a little bit speak up?
Yeah, I was just following on this tropical temperature of the LGM. So yeah, in my paper, in the emergent constraint, we only use tropical temperature, because if you use global temperature of the LGM, then the correlation with ECS is just terrible because of the influence of ice sheet. And so that's just why the temperature we had in the paper was like -2 point something. Global temperature will be much colder. That was just what I wanted to say.
Thank you. And Pascal, maybe you have a comment, and we will continue in the afternoon discussion. But Pascal, please.
Okay, so I thought it was for that. Sorry, I made some errors when I wrote on the chat. Yes, I think we are all seeking for this global temperature from different proxy reconstructions, I would say. But since the data are really good at regional scale for the paleo, we should maybe think differently and make good use on the regional scales they have, and have hypothesis testing or things like that to test the possibilities for the range of sensitivity. So find another way to do it. maybe, well, they're just an idea. I don't know exactly how it could be done. Of course, it goes through some combinations, but I'm not sure we can really get the global temperature from the reconstructions. So that's
Okay, I think it's now time to close this session. It's a pity, but we have the European session in the afternoon, continuing on climate sensitivity. We have many flash talks and we will have a discussion there. So I hope the Asian and American people will join if you can, and please, and I will give this back to the convener, the organizer. Thank you.
Yeah, okay. Thanks, Professor Abauchi, for chairing the session and the morning discussion, and everybody else who participated online and offline. Because the technicians here, we have to move the equipment to another conference room. It takes time to do the check-in. So unfortunately, we don't have more time to accommodate more discussion this morning. So please go to the afternoon or discussions tomorrow. Yeah, we still have questions in the chat box now. Okay, thanks everybody, and good night for some people.
And what time do we start tomorrow? Can you repeat that? What time do we start tomorrow? Still at 8 o'clock your time?
So it's 8 a.m. In Beijing.
Okay. See you then.
Okay, see you, everybody.
Thank you. Will you be keeping all the chat and the record for this session?
Yes, yeah, we have people doing that here.
Okay.
Thank you very much.
Thank you. Thank you very much.
哦，那就只跟线下的啊，那个现场的，我们下午的会场在仙林宾馆，但是我具体我也不知道在哪，你有谁